Welcome, everybody. We hope that you're enjoying the conference so far. We're going to go ahead and get started with our first round of Friday evening plenary presentations. Our first speaker is Geoffrey Landis. Geoffrey is a scientist at NASA John Glenn Research Center and also a science fiction author. He's going to be speaking to us this evening about memories of MIP. Welcome, Geoffrey.
Good afternoon. I'm Jeff Landis. I've been introduced, I guess, but thank you all for taking time out of your dinner hour to come listen to me. So even as we speak, the MOXIE, the Mars Oxygen Experiment, is on its way to Mars with the Perseverance rover. And I think we ought to take just a moment to realize just what an incredibly historic occasion that is. For the very first time, we are going to be manufacturing rocket fuel on Mars. This is something we have dreamed of for decades and decades. Well, Mike Hecht actually already gave a great talk about MOXIE in yesterday's session. I hope you all heard it. But I want to go back in time a little bit, talk about history and context, and maybe have an opportunity to tell you about MIP, the Mars ISPP precursor, which was the first flight experiment that was intended to go to Mars and develop propellant production on another planet. So we'll go back to 1995 and 1996. That was a few years before the Mars Society was even founded. That was before there was really a real push to go to Mars. Now, there were the crazies of the Mars underground, people like Carol Stoker and people like Chris McKay that said, yes, Mars is the next place to go. But it was a very long way away. A lot of people had been proposing for a while, even at that point, that exploring another planet would be far more effective if you could use the local resources. In particular, to use the resources to make fuel for the return voyage. At the time, they called this ISPP, in situ propellant production. Later, they widened that a little bit, started calling it ISRU, in situ resource utilization. But since oxygen is by mass the largest fraction of rocket fuel, and rocket fuel is by mass the largest fraction of what you need, generating oxygen is the critical need. But although many people talked about it, nobody was doing anything. Well, Dave Kaplan at the NASA Johnson Space Center was, in fact, doing some studies that were the design reference missions for how we would go to Mars. He was saying, well, Mars is not on NASA's exploration timeline right now, but if we did go to Mars, how would we do it? And actually, he thought from all of his analysis, it looked like the way to go to Mars would be to use fuel that you made on Mars. But he also knew that engineers are amazingly conservative when it comes to flying technology. In fact, the motto of pretty much every spacecraft engineer is, oh, that technology is wonderful, but don't fly it on my mission. I want to fly only stuff that's already been proven. So he believed the only way to get through that roadblock of not on my mission was an actual demonstration on Mars to fly this unproven technology of making rocket fuel. Well, so he proposed, in fact, to the Human Space Systems, Code M at the time, Program Operating Plan, POP, that we should fly a mission to Mars and demonstrate making oxygen. At this time, the Mars Pathfinder mission was almost ready to launch. It was a new way of doing planetary missions, with the watchword faster, better, cheaper. It was a very cheap mission. And in fact, he looked at it and said, wait a second, this Mars Pathfinder is going on the lowest and cheapest Delta rocket launcher. And he said, for a mere $5 million more, we could buy another booster, upgrade that Delta, double the payload to Mars, and fly our experiment for what by human exploration standards was just pennies. So he put this into the program operation plan and said, let's do this. It was a proposal. Well, that was MIP, the Mars ISPP precursor. And here you can actually see he was saying it's definitely rocket fuel, and there's the rocket fuel. In fact, at the time, his first program patch for the MIP mission actually showed Marvin the Martian holding the fuel nozzle to refuel your rocket. Turns out NASA put the kibosh on that. They said, no way we can use a franchised figure from Warner Brothers as part of a mission patch. So Marvin the Martian got left out of the mission patch. Well, at the same time, the Mars Pathfinder mission was flying. And when it landed in 1997, the first landing on Mars since 1976, 21 years ago, it turned out it got an amazing amount of publicity. Everybody was interested. Everybody was excited about it. So as a result, the NASA administrator at the time made a commitment. He'd say, this is so great, we're going to send 2 low-cost missions to Mars, each launch window, every 26 months. It'll be 1 lander, 1 orbiter. They'll be called the Mars Surveyor program. These would be small, fast, and cheap, and frequent. So there was the Mars Surveyor program and the mission patch for Surveyor. So they were talking about the follow-on. And actually, when you know a little bit about NASA bureaucracy, you say, wait a second, this was the human spaceflight directorate saying we're going to fly something on the science mission directorate. That's code M working with code S. This requires an agreement at the associate administrator level. So I was kind of working with Dave Kaplan on this proposal, but I was secretly thinking, man, this will never happen. You can never get agreement at the associate administrator level. Turns out the other thing that happened in that year was the discovery, I shouldn't say the discovery, the proposed discovery of life in a meteorite called ALH 84001. And that also got a lot of interest going, so much interest that all of a sudden exploration of Mars showed up on the radar of the code M and the human spaceflight people who were busy building the space station at that point, and said, man, we should think about the next thing. And they got that agreement between associate administrators. So MIP was there. We had a project. We had a mission to fly on it. All we needed was an experiment, a team to build the experiment, and to do it on a short deadline and a very tight budget. Well, okay, picking an oxygen generation. The most accessible resource on Mars turns out to be the carbon dioxide atmosphere. It's accessible because it's available everywhere on the planet. You don't have to scout for it. You don't have to mine it. You don't dig it up. It's just there, and we know what it is. It's 72.5% oxygen by weight, plus a little bit of argon and nitrogen, which we can, for the moment, skip. There's a couple of different methods of making oxygen from Martian carbon dioxide. If you're people who follow the Mars Society, I'm sure you've already are aware of several of these methods. In fact, a couple of them were talked about in some detail in the previous talk. I hope you listened to that. Selected for MIP was solid oxide electrolysis. This is essentially the same thing as the high school experiment you probably did of electrolyzing water to make oxygen come out on one side, hydrogen on the other. In this case, we're electrolyzing carbon dioxide to make carbon monoxide come out on one side, oxygen come out on the other. We do this instead of with a liquid electrolyte, it's not in solution. We use a solid electrolyte, a crystal of doped zirconia, zirconium oxide, with a catalyst on it. It turns out at high temperatures, this zirconia is conductive to oxygen ions. So if we split the oxygen on one side of the zirconium membrane, put a little bit of electric field across it, we can recombine the oxygen ions into oxygen molecule on the other side, and we've just made oxygen by splitting the oxygen off of the carbon dioxide molecule. The carbon monoxide is a waste product, but turns out there's already carbon monoxide in the atmosphere of Mars. Don't worry, we're not polluting Mars. So there's our spacecraft. That's the Mars Surveyor 2001 spacecraft, the second of the Surveyor lander missions. And there we are, sort of in the corner. It's that little box, the sort of gold-colored box on the surface of it. Little bit bigger than a shoebox, but that is the oxygen generation experiment. Actually, if you were sharp-eyed and you saw the Mars Surveyor 2001 mission patch as it was originally envisioned, you saw, hey, wait a second, where's the rover? There was supposed to be a rover on this lander. Well, in the interests of small, fast, and cheap, mostly cheap, the rover eventually got kicked off the mission. Part of that was it was hard to figure out how to get it off of the deck of the lander and put it on the ground. The idea actually was the robotic arm would grab it and actually pick it up and move it and put it on the ground. That needed a pretty robust robotic arm. Everything started getting heavy. The people at JPL said, well, it's a little bit heavier. Sorry, no more room for MIP. We're kicking you off the experiment. Turns out the people at headquarters said, oh, sorry, if you don't have enough weight to carry the rover, we're kicking the rover off the mission. This was the first of several attempts to kick the MIP experiment off of the 2001 rover. But fortunately, we had some pretty good people at headquarters that kept us on the mission. Actually, there was a reason they were so adamant in trying to kick us off the mission. The reason is the year after the agreement had been made, the then administrator at NASA, Dan Golden, said, oh, wait a second, it makes no sense that code M, the human spaceflight people, are paying for a code S flight. So tell you what, you code S guys, you just pay for everything. So even though the original agreement was that the human spaceflight people would pay for the experiment, it got moved over to the budget of code S, and the scientists did not like that. So that left quite a bit of ill will between the science program and the human program that took quite a while to get over. Well, the MIP experiment set actually comprised 5 separate experiments to demonstrate the key components of in situ propellant production. The Mars atmospheric acquisition and compression, led by Paul Karlman at JPL. The oxygen generator subsystem, led by K.R. Sridhar at the University of Arizona. He later moved to NASA Ames. The MTURC, the thermal environment and radiator characterization, led by Dave Brinza at JPL. The Mars Array Technology Experiment, led by Dave Scheiman at OAI, working with NASA Glenn. And DART, the Dust Accumulation and Repulsion Test. I was the co-I on that at the time at OAI, later at NASA Glenn. I do have to mention, of course, the overall principal investigator was Dave Kaplan. It was his baby right from the start. He brought in the project manager, Jerry Sanders. Turned out to be a very brilliant choice on Dave's part to bring in Jerry Sanders. He was in charge of getting all the ducks lined up in a row. And I have to say, sometimes the ducks did not want to get lined up in a row. Well, looking at the different pieces, let's take a look. The Mars atmosphere acquisition and compression is what collects and compresses the atmosphere. And this was a carbon dioxide sorption pump. How that works is it's a pressure vessel. It's filled with a zeolite. This is a material that adsorbs carbon dioxide at low temperature. So if you cool it down, the carbon dioxide sticks to this crystal. When the temperature rises in the daytime, it gets released. So all this really consisted of was a container full of this zeolite powder that could be sealed. So in the nighttime, we opened it up. It cooled down. Mars gets very cold at night at our projected landing location, I think about -80. Carbon dioxide gets absorbed by the CO2, just like a sponge. Then we close it up in the daytime, it heats up and it compresses the carbon dioxide. So the net result is we compressed it from the Mars pressure of about 0.8 atmospheres up to about half an atmosphere using nothing but the day-night thermal cycle. It didn't actually take any external power, except of course for opening and closing the lid on the container. That feeds into the oxygen generation system. That was K.R. Sridhar's baby, supervised by, I think, Scott Baird at NASA JSC. And it was designed to produce propellant grade pure oxygen by this zirconia electrolysis process I mentioned. Here's what's on the inside of it. What you see on the outside is just that dome. That's just a thermal dome to keep it hot, because as I mentioned, it's running at about 750 degrees C. So it is a vacuum inside, so that tiny little oxygen generation cell can stay warm. We had a power budget of 15 watts. That was all the power that we had. Oh, and we were only allowed that power during the daytime when the sun was shining. So the main purpose of the OC, of the oxygen generation, the hard part, was making sure we had enough thermal insulation so that we didn't leak that whole 15 watts out to the cold Martian atmosphere. In fact, it took about 9.5 watts just to stay warm. So the remaining 5.5 watts was generating oxygen, which it did at about 0.04 grams per hour. And that was purely power limited. We could have produced more oxygen if we had more power. A couple more experiments that should be mentioned. Again, when we put the MIP experiment together, when we first proposed it, nobody had really flown radiators on Mars. There had been the Viking experiment, got some thermal data, but questions like the effective temperature of the night sky on Mars, how much the dust impacts the ability of the radiators to radiate heat, all of these questions were really pretty much undecided. And again, that conservative engineering mentality said, you know, we'd better have some experimental data before we can propose doing this for real on Mars. So MTurk was to actually test some radiators on Mars. Well, that's important because any of these processes do reject waste heat. Process of making propellant is going to have to reject a lot of waste heat. So we needed to characterize and demonstrate the performance of thermal radiators, measure the night sky temperature. So there it is, that sort of white and gray checkerboard on the side of the MIP package. It included 4 thermal radiators, 2 black ones, 2 white ones, and 2 of them are actually hidden behind that cover. You can sort of see that in the back there, a movable cover. So these 2 would stay dust-free because we'd keep it covered so dust wouldn't land on it. And then the other 2 dust would land on in order to see the effect of dust on the radiators. I'll talk about dust again in a moment. Power production on Mars is really critically a function of, well, we need to know power production because that's how you make propellant. Rocket propellant basically consists of reaction mass plus energy, and the power production is that energy. So we wanted to test the performance of advanced photovoltaic solar cells in the Mars environment. We wanted to measure the spectrum on Mars. We wanted to measure different types of solar cells, see how they degraded, basically see how the power system would work so that we could optimize the power system for Mars. There's a picture of it just showing some of those solar cells, also incorporating some radiometers. I could point out the various parts of it, but that's the top surface of the deck. Sitting right next to MATE was the DART experiment. We'd actually done a lot of theoretical modeling of the effect of dust on the Martian atmosphere, and the Pathfinder data suggested that, yeah, that was actually a problem. So we wanted to measure the settling rate, learn the properties of the settling dust, and try some techniques to remove or at least mitigate the dust on the solar arrays. So it had 4 parts: dust accumulation monitor, it had a microscope, it had several methods to test dust mitigation. We also put the sun position sensor there because we needed to know actually where the sun was with respect to the solar cells. Here's the pieces. Dust accumulation monitor was very similar to what we flew on the materials adherence experiment on Sojourner. We had an optical microscope with a resolution of about a microscope that would allow us to look at the properties of the individual dust particles. We looked at several different ways of mitigating dust, ranging from the very simple method of, well, what happens if we just tilt the solar cells, to some low adhesion surface coatings. We also looked at electrostatic dust repulsion, where we put a high voltage between the cells and an electrode to try and pop the dust off. So there it is. That's the flight hardware. About 16 inches by 9 inches by 10 inches, about the size of a shoebox. Or for those of you in the space business, think of it as a little bit smaller than a 3U CubeSat. Weighed about 19 pounds and ran at a maximum power of 15 watts. So hidden underneath the gold, which is just a thermal coating, is the oxygen generation system, the atmospheric compression, and also all of the electronics that operates it. So the whole thing sits on the deck of the lander. It has a single cable interface that brings in our power and gives our data back to the lander. So fabrication of the MIP, actually qualification hardware for flight, was completed in 1999. It was delivered for qual testing to be prepared to be integrated on the lander in the summer of 2000 for the 2001 launch. So we did it. Tough job, short time schedule, very small budget, and we made flight hardware on spec. And there's our spacecraft, Mars Surveyor 2001 lander spacecraft, integrated in the aeroshell, ready for testing, ready to fly to Mars, except one problem. In December of '99, the first of the Surveyor lander spacecraft, the Mars Polar Lander, crashed during its landing sequence. You've probably heard about that one. Our spacecraft, the 2001 lander, was an identical copy of that spacecraft, identical in any case in terms of the entry, descent, and landing system. We had a different set of solar arrays, different type of camera, different science package. But the landing technique was identical to the one that crashed. Review board concluded that faster, better, cheaper resulted in too many cut corners, too many safety checks that were left out, and the Mars Surveyor 2001 program was postponed. A year later, it was canceled. The spacecraft that they built was actually put into storage because the 2001 spacecraft was almost ready to go. It was going to fly only a year after that. It was put into storage. when NASA came up with the Mars Scout program, in one of the solicitations, they said, oh, if you want to propose a scout mission to the planet Mars, go ahead and use spare NASA hardware. And that was the buzzword that meant, hey, we have a perfectly good spacecraft lying around. We know what's wrong with it. If you want to use it, go ahead. So that became the Mars Phoenix lander. Phoenix because it was resurrected from the dead. Unfortunately, that was a different program, a different set of experiments. They scraped off all of the experiments and put their own experiments on it.
Jeff, we have about 5 minutes to finish up and answer any questions.
Well, that's good. So although MIP never flew, the core concept was resurrected 20 years later in the form of the MOXIE package. That's the one that's flying to Mars this year. Mike Heck told you about it yesterday. Well, it's twice as big, has 20 times much more power. It produces 200 times more oxygen. But that's another story. So in conclusion, I do want to acknowledge the whole MIP team for the exceptional work. They did a great job, tight budget, tight schedule, and we were on time, on spec, on budget. I'd name you all by name, but that's too many to list, and I'd probably skip some of you. So great job, guys. Thanks. And with that, I believe I'm ready for questions.
Excellent. Thank you, Jeff. We do have a few questions for you. Raphael asks, how does the MIP demonstrate that rocket fuel can be manufactured on Martian soil for the return trip on Earth?
Yeah, well, the key was we weren't manufacturing it from the soil. We were manufacturing it from the atmosphere. And the nice thing about the atmosphere is we know it's there everywhere on Mars. So we were just manufacturing the oxygen. So for this particular case, we would have had to bring the fuel part of the propellant from Earth. So when I say rocket fuel, perhaps I should be more specific. We're making rocket propellant, but we're making the heavy part of the propellant. We're making the oxygen part. We'd still have to bring the fuel to burn with the oxidizer from Earth. So we're just making oxygen.
Thank you. Rodrigo asks, were you involved in the various ISRU oxygen extraction tests conducted in Hawaii, Roxygen and Pilot and Resolve? And do you know what came out of those tests?
Yeah, that was after the end of the MIP experiment. I wasn't part of that. Jerry Sanders was part, Diane Linney at NASA Glenn was part of that, a couple of other of the people that I've worked with. Not, however, something that I was part of. They've done actually quite a few different technologies for making oxygen. There's a number of things that are ready to try, but so far, this is the second attempt to send one to Mars with MOXIE. So we'll see how that works. But no, I wasn't involved with the Hawaii experiments.
All right, thank you. And then Anara asks, what do you think is the most important project being run in NASA at the moment and why?
What's the most important project? Wow. There's so many great things that are happening. I mean, missions to asteroids. We have Juno in orbit around Jupiter. We have a helicopter on its way to Mars, another helicopter that'll be going to Titan, and of course the moon mission. I'm in favor of all of them. I think we should go to space with humans. We should go with robotics. We should do science. We should settle space. So I'm in favor of every single one of them. They're all important. Sorry to dodge the question. I must be.
No, that's all right. It's hard
like
to place one above another. It's like loving children.
Yes.
Daniel asks, and I think this is the last question that we have time for. Daniel asks, was testing and replicating temperature and atmosphere performed?
Yeah, this was tested in a thermal vacuum chamber, looking at the temperature, looking at the atmosphere. basically went through the full qual test and then was put in a warehouse, and as far as I know is still there.
Excellent. Thank you very much, Jeff. I think that's just about as much time as we have.
Well, thank you for listening.
Our next speaker is Tabor McCallum. Tabor is the current chairman of the Commercial Spaceflight Federation and co-founder and chief technology officer of Space Perspective, and he's going to be speaking to us about Space Perspective. James, is Tabor here?
This is David. He doesn't appear to be in the list of attendees yet, so.
It looks like he may be logged in under a different name.
Okay, any clue what their name is?
I just got a message from Jane Pointer that says, "I am here, Tabor." James or David, if you could promote Jane Pointer, that would be great.
Okay. Yeah. Huh. No problem.
Do you see that name on the list there?
Yeah, I found it, but I can't. I'm supposed to. What it's supposed to do, it isn't working. First time I've tried this.
James, are you listening? I think James needs to do it because he's the host.
Yeah. I should be able to do it as a co-host, but it's not doing what it's supposed to do. Try something else. Can you text James? I'm in Singapore right now, so I can't text him.
Yeah, I'm working on that.
Okay, thanks.
Hey, James, can you promote Jane Pointer to panelist, please?
Yeah, sure thing.
Thank you.
And James, just to let you know, the hover doesn't work. I've tried all sorts of things to get her or him.
I think I'm here now.
All right, there we go. Tabor, thank you for your patience. And we've already introduced you, so if you want to go ahead and get started, welcome.
Awesome. Sorry about the name saying that, so ignore that. I'm actually Tabor McCallum, not Jane Pointer, but you'd probably be better off if I was Jane Pointer. At any rate, I'm going to talk about Space Perspective, which is a space tourism company that we've been starting up this year. And I've got a few slides here to show. Are you all seeing that screen now?
Yes,
Yeah, that
good.
looks great.
Awesome. So what we're wanting to do is give access to a edge of space experience, seeing the world from the edge of space. But I want to sort of put this in the context of pathway to how we got here. And that pathway is really on the way to Mars. So I started my career actually on this ship for about 2 years. And part of what was fascinating about being on a ship for 2 years is that's sort of the time it takes to get to Mars. And having a sense of how long that was and sailing much of the way around the world in that time period, I happened to be on the crew that was brought from that ship to do a project called Biosphere II. And what's interesting about that, so this is the mid 80s now, and Buckminster Fuller had dared the Bass family essentially to go build a biosphere. And the biosphere is, essentially the fundamental unit of life. If we're going to take life into the solar system, if we're going to live on Mars, if we're going to be a multiplanetary species, we're going to be taking our biosphere with us in one way or another. So the idea of the Biosphere 2 project was to test the idea that you could build an artificial biosphere and one day build biospheres on Mars, and that they would be self-sustaining. In the process of doing that, we built this little test chamber we called the test module to test out life support systems, water recycling, air recycling systems like it. Actually, the very first test data that was published from these early experiments was at the Case for Mars conferences. And so there was, Carol Stoker and Penelope Boston and Chris McKay were all there. And, I sort of nervously presented all of the data that we'd gathered about trace contaminants and a methane buildup issue that we had and some other problems with carbon dioxide, and sort of laid out where we were in the pathway of building systems that could go to Mars. Remember, this is the mid 80s, so NASA had never failed to execute on a mission it had been given. So the space shuttle was flying, and we were on our way to Mars, and so Biosphere 2 was sort of in that line. Also, a commercial space operation. Right now, that same test module is being transformed by Kai Statz, who is actually going to present on this later on. It's called SAM Bio 2, the analog for Mars at Biosphere 2. And they're turning this system into an analog system for Mars. And Paragon, one of our companies, is doing parts of the life support system inside of the module. So it's sort of like coming full circle. It's great. And it's going to have a big Mars yard. And you'll hear all about this later, but I'm very excited to see some of this hardware. So a bit like the Phoenix lander being reused, we're seeing this test module being reused for exploring Mars technologies. Space Biospheres Ventures was a commercial company developing life support technologies for use in exploring the solar system, and also helping us understand sort of how our Earth works. with an agriculture and a habitat and desert and the like. And I was on the design team and a crew member for 2 years and 20 minutes inside. And this is me going in, and that's the Biosphere. And I think the basic result of the Biosphere II experiment was that humans have a really hard time in isolation and confinement. And there's a great book that Jane Pointer wrote about how crazy we all went, and that there were no fundamental issues with making an artificial biosphere, that Bucky Fuller's challenge to us was met. And while we had lots of issues, all of those issues could really be tracked back to the design of this particular biosphere, not sort of the act of closing up a small biosphere. From Biosphere II, a gang of us got together and started something called Paragon Space Development Corporation, which is going great guns now and has done parts of and hardware for virtually all human flight systems, either design or hardware. There's the thermal control system on Dream Chaser, a lot of work on Orion, humidity and systems on the Boeing vehicle. So that brought together a collection of technologies for going to Mars. And one of the first things that we actually did at Paragon was take some of the principles we learned at Biosphere II about how to make these closed ecosystems and challenge ourselves with would those work in a microgravity environment? Because that was one of the things that obviously we couldn't test in Biosphere II. So we made a teeny tiny biosphere and actually flew it on the shuttle and to Mir. We bred the first animals through a complete life cycle in space, and was also the first commercial payload on ISS. So we're finding that living systems are actually quite pliable and can be rearranged and put together sort of the way we do DNA now into living systems that can support life and animals. Another fun project sort of on this path to space perspective was something called Inspiration Mars, where Dennis Tito put in a bunch of resources to look at, can we take all existing technologies and do a Mars flyby? And we had a lot of support from the Mars Society, a lot of great work from NASA, and we worked out a bunch of different concepts. And I think really showed in a big report that a Mars flyby mission is possible. And I think as one of the big dragons of going to Mars is, can you get there? And as Bob Zubrin said, this gets one of those dragons off the map. And so we thought it was really important to figure out how to do just a flyby mission. Just let's conquer that getting there part technically. And maybe the most important part of that work that we did was to actually build real hardware. We put together a system of hardware that had all the life support components that would be needed for that kind of a 500-day mission: CO2 recycling, oxygen generation, water recycling. We actually did a lot of work with solid oxide electrolysis. So this was after MIP, but before Oxy. And put it through its paces and really created an engineering baseline for the transit to Mars from Earth. And solid oxide electrolysis is on its way to Mars now. The water recycling component of that, which was based on really transpiring, much the way leaves transpire water to purify water, to get to about 98, 99% water recycling. And that system is on its way to the International Space Station probably later this year. So leading now to getting closer to balloons, there has long been a science fiction idea of taking people into space, up to the edge of space. This is 1934. And Alan Eustace, as we were talking about this whole idea of taking people to the edge of space on a balloon, said, let's do a project, and I want to go to the edge of space. So we took him to essentially 136,000 feet and dropped him at Mach 1.22 on the way back and did a lot of work in aerodynamic stabilization and the like. But what was relevant for Mars was the suit we built. This was the first actually utilized spacesuit, new design of a spacesuit built in 40 years. The American suit is still based on the Apollo suit. And of course, the suit is based on the Russian suit, and that hasn't changed either. And we wanted this to be a super rugged suit. We only had one suit, and it had to go through all the testing. And this turned out to be an interesting analog for a suit that you would use to work on Mars. We had double seals. We had really made it strong in a sense of robust utilization. This is during jumping out of airplanes to test its low velocity aerodynamic stability, controllability and the like. And you see rollerblades on the front of a spacesuit because we had to roll him out of the aircraft. So this is probably the only time you're going to see rollerblades on the front of a spacesuit. In these early tests, we would have skydivers with him to get him down to Earth safely if he couldn't actuate something. But then what became really interesting in terms of the Mars analog was the landings. They were not very graceful. As you can see, Alan did lots of tumbles and turns in the dirt, and we would dust the suit off and fix the broken bits, and we'd be out flying the next day. We did it over and over and over again with one suit, very analogous to the kinds of treatment that one would imagine a worker on Mars would, the kind of abuse that suit would get. Here's another series of graceful landings by Alan. For a number of reasons, we could never get a running or a spun landing. He always did these topples over in the fine sands of southern New Mexico. So after all that, this is the third launch. We did flights in 3 weeks. So pretty much on a 1 week cadence of flights, which is the closest to that in human flight is 6 months between flights. So we also got this to a very high operational cadence, which is sort of the key, reuse and high cadence, as I'm sure we've all heard through this conference, is a key to what we're trying to do going to Mars. And this is the very tip of the top of the balloon is inflated there, but that's a 17 million cubic foot balloon that will become perfectly round above that little speck of Allen at the bottom to give you a sense of scale of these balloons. Quickly, this is right before him releasing to supersonically skydive back. This is that initial sequence with the stabilization system deploying for the spacesuit, and then him coming down for another of these ingraceful landings. And that's the team. And it's also important to note how small a team can do these kinds of things. This is the primary and two backup medical teams. This is the launch team, all the engineers. This is the chase crews. This is what it took to pull that off. And it's a pretty small number of people, which is in large measure why we're able to do the cool things you're doing in commercial space now, because we can do a lot with a dedicated small crew of folks. We learned a lot about the stratosphere in those flights, which led to an unmanned platform at Worldview, which we started after Paragon. That on the right is about 400 feet or so. Those two bulges in the middle are ballast tanks, and this operates at about Martian atmospheric pressure. And sort of it can get up to 90,000 feet in the air, and is a really interesting example of altitude controlled balloons that could fly at Martian atmospheric pressure. So all of these sort of things take us along the road to back to space tourism. And so I think this is fundamentally on the road to what we want to do, because we need a strong base. I mean, we have the technology, right? So what I've just sort of gone through, and if you combine all this with all the other great work that's being done and Blue Origin and SpaceX, the pieces are there, but I think somebody said earlier in Alon's, is there a will and a way? And we have a way, but we really need to make space flight more accessible, create a foundation of work for space exploration, for science, make space flight simply easier to do and more commonplace. So this is the concept that we're working on. We're venture backed, and we are now really fully engaged in hiring. Now, the basic idea is to lift off from the land, go to 100,000 feet at a blazing 12 miles an hour. So it takes about 2 hours to get up there for 2 hours. Enjoy the view, do what you would like to do. Jeff Hoffman calls this the quintessential astronaut experience, the just sitting, looking out the window, slowly descend back down and splash down in the ocean. And that's done largely for scalability reasons. It's much harder to do a land landing repeatedly as an operation than it is to do a splashdown with this kind of a system. It's 8 passengers, 1 pilot. Of course, there's a bar and a lavatory. All real spaceships have a bar. And you sort of get an idea of the layout and size there. We're setting this up to be launchable from a variety of areas. We're now working with actually all 3 spaceports in Florida to launch from those spaceports. We're regulated just like Virgin Galactic or SpaceX as a commercial launch. Our operations center, first operations center, is here at where I'm talking to you from at Kennedy Center. We are in that building there at the central line of the shuttle landing facility for getting ready for launches. And we're going to have our first test flight, an unmanned, full scale, but unpressurized capsule Q1 next year to start going through some of the ConOps and other issues. This is launching from Kennedy, and I'm going to make sure I leave some time here for questions. Florida is interesting for us in operations because the stratosphere goes east part of the year and west part of the year. So part of the year will splash Atlantic and part of the year will splash down in the Gulf, launching from Kennedy Space Center. So Florida actually turns out to be a quite elegant place for us to have initial operations, and Kennedy quite iconic, and it's great to be working here. The folks here are just terrific. We also have a lot of very interesting science applications because we're doing routine profiles of the atmosphere up into the stratosphere. We're able to do measurements of things like mixing rates by doing precise measurements of carbon dioxide, for example. So there's a lot of actually very interesting global change science that we're looking at as part of the program. And then we do a water recovery after splashing down, quite analogous to what Dragon and Crew Dragon do. And that essentially the presentation on what we're doing at Space Perspective. I do think it's really important for us to make space flight accessible, and that people see that we live in a small planet with a thin atmosphere, and sort of get what Alana earlier today called the risks that we have being stuck on this one planet. And I think the more people that have that experience and give that experience to other people or transmit that to others, I think it forms the basis of how we get to Mars and how we explore space. Without public support, either people buying tickets to Mars or supporting NASA, I just don't think it's going to happen. So this is very much for us part of making space something that people think they can go do and do. So with that, I'll take some questions.
Great, thank you very much. First question is, so it's 8 passengers, and what's the cost that you're you're aiming for these flights?
So we're looking at about $125,000 a ticket. It could be more or less. We haven't set the ticket price yet. And we're also looking at a range of programs for people to fly that don't have that kind of pocket change. And actually, one of the most interesting programs, we have a partnership now with Space for Humanity. We're one of their key suppliers. And they are essentially funding leadership programs to take people to the edge of space, teachers, artists, etc. So by bringing the price down and providing a non-rocket experience, you're floating at 30 kilometers, but the sky is dark, the earth is curved. I think we can deliver an experience that's quite foundational to a large number of people.
Great. I was curious, you mentioned there was a pilot. So what is a pilot's responsibilities? Because it seems like, at least the thought is that balloons don't really require much of a pilot. So, and you mentioned the first flight is automated. So can you speak to that?
Yeah, don't tell the pilot. So look, there are certainly contingencies and something happening with the life support system and the like that somebody on board would need to have. And there is a bit of piloting associated with bringing the balloon down to the surface of the water gracefully, but the computer does a better job than the pilot, quite frankly. It's the person on board to be the adult in the room, to stop serving the drinks, and to be there in a contingency. But it's completely flyable automatically, and it's completely flyable from the ground. And so the baseline is that essentially it's on the ground flying, and there's an automatic takeover if for some reason all communications drop out. But yes, it's a relatively straightforward piloting.
With the landing in the ocean, what's the turnaround time on reusing the capsule? Like, what do you have to do to make sure there's no corrosion from contact with the salt water?
So we're really designing it a bit like a boat. It's a boat that's also a spaceship. So by using composites and designing it for quick reuse and thinking of it like a boat in that aspect of it, it looks like we're probably a day's getting it back to port and a day refurbishing, and then a couple of contingency days. So it looks like the refurb time is something on the order of 4 days. We're then looking for the next weather opportunity to launch. So we're baselining something on the order of a flight a week per capsule, with about half of that week being the return and refurb, and half of that week being the flight. I think we can get it down to much less and do some of that refurb on the trip back, things like that. But that's what we're baselining.
And the balloon itself is reusable as well. What's the turnaround for that?
Unfortunately, the balloon is not reusable, at least not at this point. So the balloon is about 8 acres of material, and it's thin polyethylene. And so by the time it falls in the water and you get it out of the water, there's not a whole lot left of it. So we're looking at ways to make the balloon reusable and recoverable. But at this point, it's the reused part is the capsule, backup parachutes, all of that, and the balloon is not yet reusable.
Okay. And you said it goes up to 100 kilometers. Is that the height, or is there going to be any modification based on weather on how high the balloon flies?
So the standard flight is actually to 100,000 feet or 30 kilometers. So
right.
and then you can, with a balloon, we've done you can get that mass to something like 110, 115,000 feet, but that's pretty much the limit of something on the order of 10,000 pounds.
Okay, great. And what's the total volume of the balloon? I assume it modifies as it goes up through the atmosphere?
Yes, so you start off with about 1% of the volume, and it expands 100-fold. And once it's fully inflated, it's on the order of 17 to 18 million cubic feet. So it's about 350 feet across, 400 feet across. So you could just about get a little football field inside and spin it without touching the edges.
All right, great. Thank you very much for your time. I think we need to move on to the next session.
Awesome, thank you.
Does anybody know if Peter is here yet?
Yeah, hey Lee, this is James. I just emailed him, but I have not heard from him yet. He did accept the invite.
Okay, well, I'll go ahead and get started with the introduction so that as soon as he shows up, he can get started. Our next speaker is going to be Peter Diamandis. He was recently named by Fortune as one of the world's 50 greatest leaders. Peter is the founder and executive chairman of the X Prize Foundation, which leads the world in designing and operating large-scale incentive competitions. He's also the executive founder of Singularity University, a graduate-level Silicon Valley institution that counsels the world's leaders on exponentially growing technologies. He's going to speak to us about the X Prize Foundation and Singularity University.
Okay, sorry for the bit of the hiccup here, but we're going to go ahead and just take some general questions while we wait for our next panelist. So if anybody has any questions, please go ahead and ask them, and we'll have the panelists that are here answer them.
There's one or two in the Q&A, but we can also have people unmute themselves. If you guys want to raise your hand, attendees, raise your hand if you have a question and we can unmute you.
To start with, I saw a question from Bruce McKenzie. He wanted to know if it was hydrogen or helium in the balloon.
Yeah, you want to take that one, Jeffrey?
Well, I think that one's for Tabor.
Is Tabor still here? I don't think he is.
Oh, okay. Would find it hard to believe it would be anything but helium. There's so much of a fear of hydrogen balloons that I'm not sure that they'd allow a large one of that size.
So Patrick Selby, I'm going to let you go ahead and unmute yourself and ask your question.
Hi, this is Patrick. I had a question for Jeff. Regarding the oxygen generator on Mars, creating methane on Mars, would that be a similar process as the oxygen generator that you guys were working on?
It turns out actually that methane on Mars is a different process. You don't do it by electrolysis. You probably do it by the Sabatier process. Those of you who are familiar with Bob Zubrin's work probably are pretty familiar with the Sabatier, where you take hydrogen, react it with carbon dioxide, making methane and water. It turns out if you're going to burn the methane, you need more oxygen than you produce by Sabatier. So you still need to do an oxygen production.
Okay, so they would probably work hand in hand then, it sounds like.
It would. An alternative would be to take some of the methane you make and then pyrolyze it, and then just throw away the carbon that you make and then use the hydrogen to make more. But yeah, probably you would use both the zirconia electrolysis and also the Sabatier.
Gotcha. Cool. Thank you.
Thanks, Patrick. Peter Clark, I'm going to go ahead and ask you to unmute and ask your question. Peter Clark, you had your hand up. Okay. Is there anything else in the Q&A panel? Okay, no. Anyone else have a question? Go ahead and raise your hand and we'll unmute you. Hikaru, I'll go ahead and let you unmute yourself.
Hi, can you hear me?
Yes, I can.
This is to Jeff. Thank you for the talk. It was interesting to listen to all the politics and how hard it was to do the ISRU on Mars. So I was wondering, what do you think, like how long do you think it takes for more various ISRU methods to be actually tested in space? Because if it was so hard for MIP, I was wondering if people are trying to do different type of ISRU, not only for propellant or fuels, but um, would you expect it would take many years for them to be actually tested?
Yes. There are many, many people who are doing ISRU experiments on the Earth. There's experiments with a lot of solid oxide electrolysis. There's Sabatier. There's reverse water gas shifts being made. The real sticking point, the hard part, has been getting somebody to fly them in a test mission on Mars. I am certainly hoping that Mike Heck's MOXIE experiment will break that logjam and people will say, wow, let's do this. But it has taken a lot of work trying to convince the mission engineers to fly the untested technologies. It's very hard. I'd love to see a Sabatier fly in a future mission, though. I really want to see that.
How many years or decades would you be your guess?
Well, we could do it on the next mission if we chose to do it.
Mm-hmm.
Right now, NASA is, I think, hoping that the next mission will actually be the sample return mission. Now, if I were in charge of NASA, I would do the sample return mission using in situ generated propellant, because I think showing in situ generated propellant and actually launching a rocket from Mars is the next most important thing, the very most important thing we could do to get a Mars mission moving. But the spacecraft engineers don't ever want to fly a new technology if they can avoid it.
Yeah. So how long do you think it takes for the era to come where many diverse set of ISRU technologies can be tested often?
Well, I am hoping that with the new low-cost launch vehicles, that the cost of doing missions to Mars is going to be reduced. We've already seen a lot more missions to Mars this year than there's ever been.
Mm-hmm.
So I hope that very, very soon, Elon Musk was saying that he was hoping to do Starship flights to Mars, not this next launch opportunity, but the launch opportunity after that in 4 years from now. And that would be a perfect opportunity to do some ISRU testing. So cross your fingers. Let's hope we can do it in 4 years.
Yeah, that's great to hear. Thank you.
I'm cheering for Elon. I hope he gets his Starship flying.
Thank you.
Yeah, you're very welcome. Any other questions? Jerry Stone, you have a question. Go ahead.
Thanks very much. As we're talking about Starship, and bearing in mind what the Saturn V could get to the moon and how little was put down and came back, I mean, with Starship, we're talking about landing an absolutely huge vehicle by comparison on the moon, and we're also talking about sending it to Mars. And okay, so once you're there, if you can make your return fuel whilst you're there, then fine. But I mean, really, the question for many people is, how do you get that much mass out there in the first place? I mean, how does Starship's capabilities compare, say, with how much the Saturn V could send en route to the moon?
Yeah, I don't know if I have a good answer to that, because I'm not sure if I've seen the details of Elon's plans. I'm pretty sure that it does involve in-space refueling. So you do many launches from the Earth just to launch the fuel to get to and land on Mars, which is one way to avoid making an absolutely humongous launch from Earth. But I'm not actually sure the details of his plan.
Okay, so we're effectively talking about Earth orbit rendezvous as
Yes.
the mission plan.
Yeah, not only Earth orbit rendezvous, but also fuel transfer, which so far has not really been demonstrated in space. But so it's tricky. I see Bruce McKenzie just answered that in the Q&A. So thank you, Bruce.
Patrick, do you have another question?
I sure did. Yeah, for Jeff as well. The original oxygen generation system that you worked on in 2000 or 2001. How is it a lot different than the sort of the MOXIE system that they're doing now? You mentioned the capacity is more, but is there fundamentally any design or technology that has changed in the 20 years?
The fundamental technology is the same. A lot of the details are very, very different. And I do have to point out that we just wanted to show that we could do it. The MOXIE project is putting out a much higher amount of oxygen, about 200 times more oxygen than we were doing. Right for those guys, good work. The fundamental technology is the same. They have a much more refined version of the solid oxide electrolysis. We also went with the sorption pump. So the zeolite basically serves as a sponge for the carbon dioxide atmosphere. They went with a more conventional vacuum pump. They're using a
Yeah, hello.
I just realized I was talking into a muted mic, so.
Sorry, that might have been my fault, Jeffrey.
They got quiet there just for a second. You were talking about the vacuum pump.
Yeah, so we used the sorption pump. They moved to a scroll pump, which is a more conventional type of vacuum pump. Probably a good move. There's a lot of technology that's been done on that type of pumps. So they're using a type of pump that has a pretty long history. It's way down the learning curve.
And I would think if you have more than 15 watts to work with, it opens up additional possibilities as well.
Yes.
Cool. Thank you.
Thanks, Patrick. Next is Pankaj. Pankaj, do you have a question?
Yes. My question is, how would the soft landing of the Starship be possible on the surface of the moon?
Well, it's a rocket-powered lander, so you'd think it should be pretty straightforward on the moon. They use the atmosphere for stabilization. They use the little fins at top to keep the top side up as it's moving downward. But there's been a lot of people who have looked at the question of actively controlled vertical landing, and it seems to be a solvable problem. So it's a rocket-powered landing.
Okay. Right. Thank you.
Okay. Thank you, Pankaj. Jerry Stone, do you have another question?
I do actually, and it's on a completely separate area. Jeffrey, you're a published author, not only of books, prize-winning books, but also poems. Now, yesterday, Robert said, Mars needs poets. So, can I ask you, do you have any poems in space?
No, unless some of the people who have brought reading matter to the space station haven't told me about it. As far as I know, none of my material is currently in space or has been in space.
All right, in that case, I can make a claim. I am an interplanetary poet. Specifically, I am a Mars poet because a poem of mine is currently in orbit around Mars on the Maven spacecraft. My name is on all kinds of spacecraft, but for Maven, the outreach team asked for something extra. They wanted people to submit a poem in the form of a Japanese haiku. And my submission went, "We look out to space and Mars beckons us onward. Our future lies there." And they liked it, and it was one of the few chosen to be placed on the craft. And so on the back of my business card, where it said fellow of the British Interplanetary Society and this and that, and at the bottom it says interplanetary poet, which is rather nice.
Hey, first interplanetary poet, at least first one I know of. That's cool.
Thank you, Jerry. Mate Ravas, would you like to ask your question? Mate Ravas, are you able to ask a question? We cannot hear you right now. You're unmuted though.
Hello.
Yes, go ahead.
Oh, there you are. Apologies for that. Before I ask my question, I just wanted to ask that the previous question was lovely, so thank you for asking that as well. I wanted to go back to the sciencey bits and ask about the atmospheric reusing of atmosphere. And I'm a rare breed. I'm a biologist in the panel. So I'm apart from oxygen, I'm very interested in concentrating nitrogen. So be interested would it be possible to concentrate and kind of harvest nitrogen with the technology that's used in MOXIE and MIP?
You could. Actually, the interesting thing about MIP was the sorption pump that we used to concentrate the carbon dioxide. The exhaust stream for that was mostly nitrogen. So we were also purifying nitrogen out of that. But probably if you want nitrogen out of the Mars atmosphere, my guess is probably the way to do that would be to use a liquefaction. So essentially distill it out of the atmosphere the same way you would distill it out of the Earth's atmosphere to make liquid nitrogen. But with that said, I should say I've never actually looked into the question of how do you get nitrogen. Mostly we have the question of if we're trying to get carbon dioxide, how do we exclude the nitrogen?
Okay, I think we could take one last question. William Gardier. William, would you like to ask your question? Okay. Well, I think we have everyone for the next panel here.
Would you like me to go ahead and make those introductions?
Yes, please.
All right, excellent. Thank you everybody for those questions, and Jeff, thank you for your answers. Our next panel consists of Nicole Willett, Robert Zubrin, Carol Stoker, Chris McKay, and Ruud Abramovich. They're going to be speaking to us about the search for life on Mars. Welcome.
Hello, everybody. Hello,
Hello.
Nicole.
Thank you for joining this all-important panel. And thank you, Dr. Zubrin. He was a surprise. He wanted to join. And thank you, Dr. McKay and Dr. Stoker. And it's so nice to meet you, Dr. Abramovich. So today, I want to ask questions sometimes to certain scientists, and sometimes you can all just chime in as you wish. And I would like to start with Dr. Stoker and Dr. McKay about questions I got from Dr. Gil Levin. He sent me some questions.
Great.
You both spoke of him yesterday, and I am one of his biggest fans. And he would like to know two things. Has phosphine been sought or found on Mars? And is there any known factor preventing current life on Mars? So those are his two questions. Have at it.
Carol, are you there?
Well, I'm trying to figure out where my video is.
You're on the moon, so I would try
Yeah, I can see the
Sea of
moon.
Tranquility.
See my face. Oh well. We'll have to
While
go with
we're
that.
waiting for Carol, can I just interject two comments, Nicole? One is the previous question about, from the last event panel, how to get nitrogen on Mars for biology. One would not extract it from the N2 in the atmosphere. We know there's nitrate in the soil, so you just dig it up. It's pretty thin, but it's much higher relative concentrations in the soil as nitrate. And plants and microbes will be happy with nitrate. The other thing I wanted to do is just say hi to Rude. It's great to see you, friend and colleague for many years, spaceward bound, and so on. But anyway, Carol, if you wanted to address the question Nicole raised, then I will add my comments too.
Yeah, so what you're going to see is the moon, and you're not going to see my face because for some reason the background is there, but the person is not. I don't know why. It's changed. It used to work. So the question was, better remind me.
Has
phosphine been seen?
Been sought?
To my knowledge, no. In fact, phosphine has suddenly been seen on Venus and is now a big buzz that Venus is habitable because they've seen phosphine on Venus. I know of nothing that would have, no report of phosphine on Mars.
Okay, thank you. And Dr. Levin also would like to know, is there any known factor preventing current life on Mars?
On the surface, yes, there's a few items preventing life on Mars, but on the subsurface and perhaps underground lakes, there are many places where life can be sustained and can be very happy on Mars.
Wonderful. And since we brought up Venus, I'll ask Dr. Abramovich the Venus question. I would like to know, what are your thoughts on the buzz around life on Venus, and what type of life could it be if there was life on Venus?
So Venus doesn't have really a good habitable area above surface. Closer to the ground, you have really high atmospheric pressure and you have high temperature, which we know now from hydrothermal vents. It's actually a place where life can be alive. There's a lot of nutrients going around in Venus that goes for it. But the issue is a lot of the sulfuric acid, which is in the atmosphere, and that's also apparent in the upper atmosphere. And that's pretty deadly. Like the pH levels are very, very acidic. And the water availability is very, very low in Venus. So we think it's not a good place at the moment for life. But having said that, I would love to have a Venera D mission going to Venus again and, putting our technologies up front and seeing what's happening there. Today, we can do a much better mission at exploring Venus on the ground and also in the atmosphere. So as an explorer, I would like to go and check it out for sure.
Yeah, there's been some talk about maybe some life in the clouds on Venus. So it'd be interesting to see if that happens. And sorry, go ahead.
It's okay. Go ahead.
Dr. McKay, yesterday in your morning plenary, you spoke of a non-life detection mission to Mars, and also whether there was a second genesis on Mars. Can you explain how a non-life detection mission may miss out on identifying a second genesis that utilizes a different genetic material than what we would be looking for?
Okay.
And how that may affect a human mission to Mars?
Sure. That's very good question. Very good point. And the 2 points do go together. The point about a non-life detection mission is really a check the box exercise, if you will. We want to put humans down in the equatorial region of Mars, in an area which most people, look, Carol's got a good picture of it as her background there. Most people think that these areas of Mars are lifeless. Gil Levin's results notwithstanding. We think that they are highly oxidized, very low water activity, even lower water activity than the water activity in the lifeless clouds of Venus, and exposed to high UV and even high ionizing radiation. But we don't know for sure that it's lifeless. One reason we don't know for sure is Gil's results, for example, can be explained by biology. That's not most people's preferred explanation, but I think it would be premature to be dogmatic and say, we know there's no life on Mars. It's safe to bring humans back. So I think there's going to be a requirement to either quarantine the astronauts from the Mars dirt or on their return to Earth, or conduct a due diligence experiment on the site similar to where they're going to confirm to some level of reasonableness determined by scientific community that there is no life. Unfortunately, the Viking results don't meet that standard. None of the subsequent missions meet that standard. So we need a mission, in a sense, to show that there's no life in the equator of Mars, right? If such a mission was a hitchhiker along, say, a SpaceX large lander, the total cost of it would be probably $100 million, a drop in the bucket compared to any incremental cost on human exploration. So that's what I mean by a no life detection. And as Zubrin so nicely pointed out yesterday, that would not prove there's no life on Mars. Of course not. It would just prove that locally and temporally there is no life within some reasonable detection limit, making it safe in a sense for astronauts. But there could very well be life, as Ryuk just indicated, deep below the surface in an aquifer, happily metabolizing along like we know is occurring on Earth today. And that life would not contaminate astronauts. It would not impair their ability to return to Earth, but they could discover it through deep drilling. And then they could maybe discover that it's very different from life on Earth. And that would be very wonderful. I hope to live to see that day. Well, even if I don't live to see it, I can imagine it, because that would tell us that there's 2 life forms in our solar system. N is greater than or equal to 2, where N is the number of life forms in the universe. And that is really quite a different question than the biohazard. How would we, your second part of your question, Nicole, is how would we know that it's a second genesis? And I think the operational answer is we would see if it maps on the tree of life. All life on Earth maps onto a tree, a phylogenetic tree showing the relationship of that life. Viruses sort of float around the tree, but they are on it. They're in the tree, maybe in the bushes or the roots or somewhere, but they're in there too. If we find life on Mars and it doesn't relate to that tree at all, even if it's made of carbon and water, and even if it's made of the amino acids, if it doesn't relate to that tree, it's a second genesis, N equals 2. And we have achieved an amazing scientific step forward in our understanding of life in the universe. And that would be wonderful.
It would be great. And I have a question for you, Dr. Zubrin, since you brought up some of the stuff, Dr. McKay, about what Robert Zubrin pointed out yesterday. Can you talk about the planetary protection? I know you have some strong feelings about that and life on Mars, and how NASA and other space agencies are, so worried about the planetary protection. Can you delve into that for me?
Well, sure. But see, I have a somewhat different point of view than Chris on this issue, because he wants to send people where there is no life, and I would want to send people where there is life. Okay, that is, I believe that the purpose of sending astronauts to Mars is not to send them to the least interesting places, but to send them to the most interesting places. And certainly, if we sent a life detection experiment to Mars, I would want to send it to the place where I had the best chance of finding life. And as Ruth said, on the surface, it's a pretty outside chance, but you might have a chance if you sent it to the edge of a glacier and you could drill down very easily through a glacier, and maybe there's a liquid layer at its base. That has a chance of being a biologically active area within easy reach of an atmosphere. Of course, if we could drill down 1 kilometer and get to the groundwater, that's the best chance. But on a first human mission to Mars, your best chance of finding life would be, in my view, under the ice rather than under. So at mid latitudes, 38 north, there's glaciers. That's as far south as San Francisco is on Earth, about where Chris is sitting right now. So that's a dangerous area, Chris. There are microbes there. But the yeah. But to be clear, look, the fact that there's life somewhere doesn't mean it's a pathogen, okay? And it's really unlikely we're going to find bat viruses on Mars, okay? Because there's no bats there, and you know, or any related megafauna or megaflora for that matter. And so the idea that we'll find pathogens that are adapted to attacking animals like us it makes no sense. And furthermore, as Chris said, you can't prove a negative. If you landed a lander and you picked up a sample of dirt and you examined it in various ways, it wouldn't prove that there wasn't microbes in the dirt 10 meters away. So to anyone who actually thought this was an issue, you would not prove anything. So I'm all for sending life detection experiments to Mars. And if human missions are delayed, this to me would be as best as we can do, send robots to find life. And if we can find life or anything looks like life, then definitely that's where I want to send the people. The idea that any dirt from Mars represents a biohazard. We have rocks from Mars landing on Earth all the time. Trillions of kilograms of rocks from Mars have landed on Earth since, 3.5 billion years ago when there was liquid water on Mars. And, one thing we found from the Allen Hills meteorite examinations, Professor Kirschvink found this, and through his examinations, was that major parts of that rock during its entire career of ejection from Mars, cruise through space, and re-entry and landing on Earth had never been raised above 40 centigrade. So that if there had been microbes in those rocks, they would have survived the trip. And so if the Red Death could come from Mars, it's already here. And this idea that we should sabotage the science of human exploration out of fear of going to interesting places, just as the Curiosity mission has already been degraded by not letting it go to places that it looked like there was water seeps for fear of planetary protection issues. And then, so that's the back contamination. And the idea of quarantining the Mars sample return and even destroying the sample if they found that containment had been violated is so crazy. It's like, the customs officers looking in the trunks of everyone's cars coming into the country from Canada, searching for Canada geese, when meantime they're flying across the border by the millions on their own. And then there is one other issue, though, that I've heard raised by astrobiologists, some of them, at various conferences that I've attended in the recent period, who were not so concerned with this back contamination issue, but with the forward contamination. That is, their argument was, we don't want to send people to Mars, because if you send people to Mars, you're sending microbes to Mars. And then how would you know that if you found microbes on Mars that they were there before you were there? Well, how do we know there was life on Earth before we got here? We know because there's a fossil record, okay? If there was life on Mars before people got there, they will have left fossils and other biomarkers. So if you find life on Mars, which is different in any fundamental way than life on Earth, for instance, it doesn't use DNA, it uses some other information system, well, then you know it was indigenous. If you find a life form that does use DNA, but it is unfamiliar with any kind we've ever seen on Earth, then it's also indigenous. If you find a life form on Mars, which is identical to familiar bacteria on Earth, but you also find biomarkers, then it's indigenous. But if you find life forms on Mars that are identical to Earth life and no biomarkers, then yeah, you brought it. So we can easily tell what if we find life on Mars, whether it was indigenous or not. And to think that there could be biomarkers on Mars and not be indigenous life, it's like creationism, who say, you know, how do we know that there was ever life in the prehistoric past, because God could have created the Earth with the fossils in it in order to test our faith. So, you know, so I don't see any merit in the planetary protection arguments in either the forward or back contamination cases.
So
And
there is
rather-
a spoken like a non-biologist.
Exactly.
Non-biologist.
But that's okay.
Well, yeah, but
Spoken like somebody who doesn't know what he's
Supervisor,
talking
we're not
about
here,
and is monopolizing the conversation, spewing out dogma instead of focusing on the issues. This panel, Bob, is the search for life. It's not a
Yeah.
rant about your particular issues with planetary
hey,
protection
excuse
policy.
me, I was asked the
Forward
question.
protection has got nothing to do here. You're just a guest on the panel. Pipe down and listen.
No, okay, stop it, Chris. I'm
I
being very
think,
polite to you.
okay.
Thank you, Nicole.
That's good
Take
for
charge. Thank you.
I think Dr. Abramovich had something she'd like to say in response to Dr. Zubrin, and I was actually going to go to you next anyway. So go ahead.
Thank you very much. Thank you. It's a fascinating topic, and part of my recent work is actually addressing part of this issue. So one of the things I've done so I'm an astrobiologist. I work with stromatolites in Shark Bay and extremophiles, and recently I'm into cross-contamination issues, which is exactly the point here. And one of the things I've checked in the last a year or so in an analog mission here in Israel is exactly the issue of how you monitor a contamination situation on Mars. So you have a crew of astronauts going on Mars, and they're coming with their own bacteria. Their equipment's going to have a few spores on it. Everything is fine. So one of the methodologies that I'm looking into is exactly checking out from a spatial and temporal point of view how much contamination is going into the ground from the astronauts and their equipment, but also backwards contamination, looking at the extreme environments and coming back in. So I totally think that we should go to Mars. I totally think we should check for life there. There are many different technologies today to check out if it's indigenous life, if it's not, what type of shapes. But also you have to understand from an astrobiologist point of view, 4.5 billion years is a very long time for a lot of evolution to happen, and a parallel evolution. So even if we find something that is different from what we like, we can still, I think we can detect it today. We are quite aware of all the different biological pathways there are there. We're not 100%, we don't know everything, but we have the technologies to go and check them out. So if you go and you monitor what's happening with the surface, with the subsurface, and you do this on a spatial grid in a temporal fashion, you can check the dynamics of what's happening because of the astronaut crew, but also how the environment would affect it back. Now, sending samples back to Earth, I was always an advocate of it's okay to bring samples, but not to Earth, but perhaps for the International Space Station or any sign of an outer space signpost designed as a biohazard level 4 lab or something like that. And now we have the capabilities of flying PhD students and scientists to the ISS to do the work if needed. So that would be some sort of a more secure fashion than actually bringing the samples back to planet Earth if we're, afraid from that point of view.
So I would like to bring up what I think is completely missing in Robert's analysis, and that is He's thinking of it only in terms of pathogens. We're going to get the Andromeda effect, you know? And it's to me, the much bigger risk is not pathogens. It's alien invaders. It's invasions of things, microbes, most likely, that are sufficiently evolved or different, whether they came from Earth or Mars and Earth shared a common origin or not, but they are sufficiently changed that when brought back to Earth and getting established on Earth, they might upset the microbial balance of the biosphere. And the microbial balance of the biosphere is actually what controls the air we breathe and the conditions that we're living on. If you start messing with that, it could be very catastrophic, much more catastrophic than a disease. And until we actually know that that is not a risk, we should not be bringing stuff back from another planet. Full stop.
Let me amplify what Carol said with an example. Rabbits in Australia are not pathogens. They're not dangerous. They're cute and cuddly. Some of my best friends are rabbits in Australia. So it's not the problem that the individual organisms are going to attack us. As Carol said, what they've done is upset the ecology. Now
we have lots of examples of that on Earth. Yeah. Lots and lots.
And I think the point is not that we cannot bring a sample back, but we have to bring it back in a way that's contained and in which it can be carefully and safely transferred to a containment facility, as Riu was saying, right? We know how to deal with dangerous organisms. We do it on Earth all the time. But if the astronauts are coming back with dirt in their boots and dirt in their lungs and dirt in their hair, that's not an easy thing to contain. And so my point here is that we have to resolve the question of sample return to Earth before astronauts are coming back to Earth. Now, we can resolve it by bringing a sample back robotically and searching through it carefully and so on, or we can resolve it in situ on Mars at much lower cost with a non-life detection mission. But the point is we need to resolve that question before astronauts are coming back, or the knock-on costs and effects to the astronaut program will be enormous. Think of the costs associated with the quarantine of the Apollo astronauts. And now amplify that by orders of magnitude, because it's coming from a planet where there's a real risk, not just an imaginary go out and shake the president's hand and then get back into a container, where there's a real risk. And so I think that from a purely cost benefit point of view, the human exploration program needs to take this question seriously in terms of when the phasing is between humans going to Mars and sample return. Now, it wasn't that many years ago when the phasing was simple. Neither sample return nor humans were going to ever happen, so we didn't need to worry about it. Now what's happening is there seems to be a sample return program almost going in at NASA, and human exploration is racing ahead. All good news, but no one's thought through how does this play together in dealing with the very real issue of sample return.
So, well, let me just say in answer to that, just briefly, as far as microbial invaders attacking our microbes are concerned, once again, SNC meteors have been coming to Earth for billions of years, and somehow the Earth's microbes have taken care of themselves. But in answer to what Chris just said, I actually agree with you. I agree with your course of action, not with your motivation. That is, I actually think that a much more effective robotic Mars exploration program would send a large number of rovers to Mars, to a large number of locations with all sorts of different suites of instruments, and do all sorts of studies in situ. And I think that's going to tell you more about Mars, including the possibility of finding or not finding life on Mars, than a sample return would. So I'm actually there as far as that's concerned. That is, I'm not that excited about sample return. if we're thinking in terms of a fixed or reasonably fixed budget of a robotic Mars exploration program, I think we'd have a much richer program with large numbers of rovers to large number of places with lots of different instruments looking for all kinds of things. I don't think, I mean, look, if you're going to do sample return, the whole argument for sample return is you're bringing the sample to Earth and where it can be looked at in 1,000 different university laboratories with all sorts of instruments that are not available in a limited facility, such as the space station. So you're going to do sample return. You want to bring the sample to Earth. But if you're not prepared to bring the sample to Earth, you shouldn't be doing sample return. You should be doing in situ science in a much richer and more diverse way. So as far as that part is concerned, I'm with you. I'm all for life detection experiments. But I don't think life detection experiments are useful in trying to prove that there isn't life on Mars, because if you're going with this what if scenario, which is really what you're doing, you're going with very low probability risks, but you're saying if there's a finite possibility and it could have a catastrophic effect, you know, reducing it from 1 in a million to 1 in 2 million chance doesn't really change the math very much here. I think we should be sending life detection experiments to Mars for the purpose of detecting life, and then following that up with people to study that life.
Okay, so thank you. I would like to follow up on something Dr. McKay said about bringing back a sample return and containing it. You know, in 1996, Dr. David McKay came out with his team and said, we found this bacterial fossil in ALH 84001, the meteorite. And it's still being debated to this day, back and forth, back and forth, back and forth. So if that is the case, and we bring a sample return from the cache from Perseverance in a few years, whenever that will be, and then we study it for 20 or 30 years, and argue back and forth, how is that going to affect a human mission to Mars?
Well, you know, you've raised some very important points, Nicole. First, on the meteorites, ALH 84001 and all the other meteorites we have from Mars are volcanic rocks. It appears to be that those are the only rocks that can survive the ejection into escape velocities. They're not very good samples for a search for life, so it's not really a good approach. And the controversy behind David McKay, who, by the way, I'm related to through a least common universal ancestor, 3.5 billion years ago. What they found was interesting evidence of water activity, and they sort of stretched it a bit, and they got in trouble, I think, on that. But the rock is very interesting, and it's a window into early Mars that was wetter than the current Mars, that's for sure. And the meteorites in general, like that. Bringing a sample back, I think, if I was in charge of the sample return program, the first sample I would bring back would just be a grab sample of the loose dust, the same kind of loose dust that Viking sampled, the same kind of loose dust that the astronauts are going to breathe, the same kind of loose dust that is inevitably going to get carried back with astronauts. And I would bring that sample back because that's going to be important to the engineering design of the human habitat. And it will also be in a very important achievement of due diligence in life detection. We look at that dust and say, hey, there's nothing alive in it. It's safe for the astronauts to breathe this. It's not going to make them sick. And it's safe for them to bring bits of it back home, inevitably, which they will. Right. So the first sample return in the program that I would outline would be a grab sample of that. Now Perseverance is not going to do that. I don't think they even bring any of the loose dust back. They just bring rock cores back because it's a mission driven by hard rock geology. So I'm not sure it's going to really give us much insight into life on Mars now or ever. I think it'll give us a lot of insight into petrology of the volcanic rocks on Mars. And that'll be good for a paper or two in JGR or Meteoritics and Planetary Science, maybe even Nature Science. But I don't think it's going to give us much about biology. Now, I may be wrong, and maybe the instruments on the rover itself will find very interesting traces of carbon and biomarkers that would, make us really want to have that sample back. But I don't think so. I think that we're going to find that they're rocks, They have mineralogy, like the rocks that we've been studying on missions to date. And the geologists will love to have it back, but the astrobiologists will not. And it may actually undercut the motivation to spend the money to bring it back. You may analyze those rock cores and decide they're not worth bringing here. Just leave them there on Mars.
Yeah, so actually Adrian Brown gave a presentation yesterday about they're going to search for stromatolites, right? Well, that's a very optimistic scenario that they're going to find stromatolites. But what I think they could find is evaporite deposits. And that is a sample that I think we should be pushing for. That if they find evaporites, in particular halites, that they bring that back. Because that's probably the only place that you got a chance of having a modern biological signature in the place that they're going.
Is the core capable of sampling halites if they came across a salt flat?
Yes, I think it is.
Okay.
So I was going to ask Dr. Stoker, yesterday during your plenary, you showed the slide of the climate model of the thermodynamically possible pure liquid water on the surface of Mars. I know that was a mouthful, but can you explain, and maybe Dr. Abramovich can come in on this as well, how is that important to the potential for finding extant life on Mars? And could that help in that search, knowing where those areas are?
So I think what you're getting at is that in order to look for a biological signature that you're going to have any hope of finding, you have to go to an environment that's habitable. That's actually been recognized for quite some time. It's just that where are those habitable environments is slow to get acceptance. I think we have finally started to convince the community that the circumpolar icy deposits on Mars, where we're trying to send the icebreaker mission, are habitable environments, or at least sometimes they are. They're not currently habitable environments, but they have been habitable in the last 5 million years. So the ice is certainly one of the attractive places that you would want to go to look for life. And the ice is by itself and at its current state, quite possibly too cold for biological activity. So it might have periods where biological activity can occur as climate goes through these cycles, which are actually pretty high frequency cycles. So, time scales of 100,000 years, you get really radical climate change on Mars. So I think the icy deposits are a very high priority target. I also think that the salts are an interesting and another plausible target. Because these kinds of salts and salts that occur on Mars, like perchlorate, are very hygroscopic, and they will pull water out of the atmosphere when the atmospheric humidity gets to something like 75%. So that is less than is required for frost to form on the surface. And we do see frost forming on the surface. But those hygroscopic salts will pull the water vapor into the salt crystal and actually fluidize the salt crystal itself. And you can watch this under a microscope. You can watch a salt crystal suddenly turn into a blob of water.
Right, like on the Phoenix
conditions.
Like on the Phoenix, the struts of the legs of the Phoenix lander, the salt was pulling the water into the globules on the legs.
Yeah, well, Phoenix lander leg was actually, I think, highly overinterpreted by the person who wrote that paper, because basically you had jets, the landing jets themselves, which were at something like 1,000 degrees, were heating that water ice and causing it to condense on the lander legs. So, that was a highly non-Mars-like environment for the time scale that those drops formed. Right. And were those drops or not, I think is also speculative, because the camera that you were taking the pictures with was super low resolution, and you couldn't tell if that was a crystal or a blob.
Okay. All right. So I was going to
Those images.
Oh, thank you. I was going to follow up with Dr. Abramovich. What kind of extreme organisms could live in a very cold, very low humidity, salty area on Mars or on any other planetary body for that matter?
So we usually find extremophiles in different areas on planet Earth that are very capable of living in the conditions you just mentioned. And each one has their own mechanism, starting from the physical niche where they reside, for instance, and then goes to how their membrane is formed, what kind of enzymes they're working with. And you can see these modifications even in their own genetic code. It's really hard to say what kind and how they look. Most probably they're going to be microorganisms because they are best adapt. Some microorganisms have like this biofilm, like a gooey stuff around them that gives them their own, humidity and nice area to develop. Caves are especially a big wonder because some of the microorganisms there actually evolve into introducing minerals. They look like minerals. They introduce minerals into their organelles, internal organelles. And we really have a spectacular diversity of life here on Earth. And we have discovered a lot in the last decades using molecular techniques and very interesting techniques. What I'm very much interested to see is a mission, whether to the moon or to Mars, which will include more molecular tools, more microbiology attitude. I have to tell you that when I go to a field expedition, there's a big difference between geologists and how microbiologists sample the area. So today, it's very clear that the people behind the amazing science that has been done on Mars are very much from a geology background in that area. But there are so many things today that we have learned how, as a microbiologist, you need to approach an area, how to sample it, how to not disturb the life as it is in its own environment, and make sure that the sample you're taking is actually a good representation of the area that you're looking in. There's so many different things you have to pay attention to, which geologists are not, as they have their own issues to look at. From a marine biology perspective, we have a lot of new technologies today that can go very deep, very into really high pressure areas, that can explore autonomously big areas, whether it's underground caves or, in oceanography, we have gliders. We have sort of like an in situ microscopes today in marine biology. They're called cytosubs. And basically what happens is that this really nice thing, it stays underwater. It can attract the water inside, and it can beam a laser onto any particle that's in the water stream. And then you can get a lot of data out of that wavelengths that come out. You can know if there's chlorophyll, if there's something else. It takes pictures while it's doing it. So all these things could be used perhaps in a mission in which you take some samples from the dust, as Chris said before, and all these things, and you can sort of like dilute them with a bit of water or a bit of liquid, and you can check out, and all these data can be transmitted back to planet Earth. Having said that, all these things, and NASA Ames have done a spectacular work in looking for equipment that can do several different types of tests and find these life signature. I just want to point out that we do have life signature today on the moon that could be a good exercise ground for that. And that's for your consideration.
Awesome. I was going to ask about the NASA scientists. I don't know about the Israeli Space Organization, if they would have any plans for this. But I was going to ask if NASA has any plans to send a DNA sequencer to Mars, because a few years ago, J. Craig Venter proposed that, and there was a bunch of articles about it, and I've reached out to his organization several times to no avail. Do you think that would be a worthy mission, send a small DNA sequencer, since they're getting smaller and easier, and pretty much anybody can send away for their DNA for $50 these days? What do you guys think about that?
Nicole, that's a very good question, and it's a very good idea. And I would just change your question a little bit.
Okay.
Can we send a sequencer to Mars that could sequence, among other things, DNA? And the answer is yes, and we should. There's recently been invented so-called nanopore sequencers, in which the molecule of interest is drawn through a little tiny pore, and it's sequenced that way. And it can be used to sequence DNA and RNA. And there's a company, I probably shouldn't name the companies because that would give NASA endorsement, but there's companies that are making commercial units that are the size of thumb drives, which can be used to sequence DNA with this nanopore technology. But the important point is that this would sequence any linear molecule, right? So a general argument has been made by Steve Benner, a very brilliant biochemist, that life must have a linear molecule to store information. It doesn't necessarily have to be DNA, but it has to be a linear polyanionic molecule. It's a very elegant argument. And for those of you who don't know much about it, you can read up about it. It's worth a study. So even if life on Mars does not use DNA, let's hope it doesn't, that would be very interesting, but it uses some other different kind of linear polyanionic molecule, as Benner is suggesting is required for life to have storage capability, information storage. This nanopore sequencer would still sequence them. So we're not proposing to do PCR, for example, which is specific to DNA, or to do any kind of sequencing that's specific to DNA. I think that I'd be disappointed if we found DNA on Mars. I want to find something interesting and different. So we've been focusing on these nanopore sequencers and trying to develop ones that will survive space flight. The challenge is making them rugged enough that they can survive a long trip to Mars and operate under Martian conditions, et cetera, and not being babied in the lab. And we've made great progress. So now your specific question is, are we planning to do that right now? There's no mission planned. Even our icebreaker mission doesn't include one of these, although we discussed it. It's not, the technology's not quite ready for flight, but it's getting there. And we will soon, I think, include these sorts of things in our missions.
Thank you. And speaking of Dr. Benner, I have a question here from Bob Bruner, who I think sent his questions out to everybody a couple weeks ago. He was asking about Steve Benner's theory of life starting on Mars because Mars had the boron to stabilize the ribose and RNA versus the Earth, which didn't have the boron, and panspermia, and maybe we came from Mars. I think several people have now proposed similar theories. That's open to anybody. And if you want to argue, more ratings. So go ahead.
Well, there's no evidence, plus or minus, that the life that is on Earth did originate on Earth. Okay, it might have, but there's some questions about that, going back to Arrhenius, in that the simplest free living organisms we find on Earth are bacteria, which are actually extremely complex things. And so, he brought up the idea that it could be an immigrant phenomena. Now, his panspermia is discredited because he believed that the universe had always existed and therefore life had always existed. And so the origin of life for him was not a meaningful question. But if we don't adopt that idea, but simply say, let's open up the constraints on what the conditions were where life originated. Okay, because if it did originate somewhere else, there could have been different conditions. There was an experiment done in the 50s, the Uri Miller experiment, where they synthesized a whole bunch of amino acids. But people said, well, this is not relevant because the conditions you had in your experiment were not those of the early Earth. Well, perhaps they were those of the place where life did originate. So it's very interesting to go to Mars because, okay, if we find a different kind of life, doesn't use DNA, uses a different linear sequence, that would suggest independent origins, well, clearly independent origins, but that would suggest that life on Earth could be an indigenous phenomenon because we have two separate examples of independent genesises. If we find identical life on Earth and Mars and no prior evolutionary organisms, that could suggest they're both seeded from spores from interstellar space. If we find life on Mars that is of the same general type as Earth life, but also including more primitive organisms than bacteria, then that would say that life on Earth came from Mars. So there's a number of possibilities here, and the only way to resolve it is to go and look.
This is really quite remarkable. I would have given exactly the same answer as Robert Zubrin. I think this is the first time we have ever been in agreement. The only difference is I would have been shorter in my response.
Thank you. That's good to know. We're moving on to the same page. Bob Bruner also wanted to know about how you guys feel about the Murchison meteorite and several other meteorites now that have been found containing amino acids and other organics. And in my opinion, I feel like the building blocks of life are everywhere we look. We find them in comets, meteorites, everywhere. There's enough chemicals, minerals, molecules on Mars to have life survive there under certain conditions. So what do you guys think about, could life be everywhere? Do you think life is everywhere? What are the odds of us finding life on Mars or going to Proxima b and finding life there based on the amino acids and organics we're finding everywhere we look?
Well, I think, Nicole, that is one of the reasons why we may be optimistic to find life, why people like me and Carol and Reut are spending basically our whole careers devoting to that search. We don't think we're wasting our time because things like these meteorites, but that is very different from saying we have proof of life. We only have proof for one example of life on Earth, one. N equals 1 is all we know. Of course, we think that N must be larger than 1, and the meteorites and the organics and the Miller-Urey synthesis and Bob's comments about panspermia and the ability of rocks to carry life from one world to another, even one star to another, are all reasons for hope that N is greater than 2. But if we're going to be scientists, we have to carefully differentiate hope, which may motivate us, and the facts, which is what we have to put in our papers. Bob.
Okay. So I would just add to that one thing. There is one outstanding fact in this whole field, which is this, which is life appeared on Earth virtually as soon as it could. We have fossils going back 3.5 billion years, arguable ones going back 3.8 billion years. So life appears on Earth as soon as it could. And that suggests really only one of two possibilities. Either the processes that lead to the development of life from chemistry are highly probable and it happens as soon as it can, in which case life is very common in the universe, or life is floating around in space and prepare to take over and land as soon as it finds a place that can accept it, in which case life is very common in the universe. So those to me seem, that is the central evidence in the case is life appears as soon as it could, and it either appears indigenously or it occurs as immigration. So I think it's very probable that life is extremely common in the universe.
Once again, I want to agree with Bob and actually commend him on a short answer. The way we test between his two choices, rapid genesis and spread, is look at Earth compared to Mars, compared to Enceladus. If we find life on Mars and Enceladus, and it turns out to be the same as life on Earth, that nails it as cosmic interstellar panspermia. If we find life on Mars, life on Enceladus, life on Earth, and they represent 3 distinctly different biochemical systems, that nails it for his other hypothesis, which is that rapid, easy origin of life in suitable environments. So the way to test, the way to choose between models, the way to choose between hypotheses is go get more data. The only place we're going to get that data is our solar system, unfortunately, Mars and Enceladus. So let's go.
And that brings me to my next group of questions, life on Europa and or Enceladus. I did a paper on a project on this many years ago for my culminating project, and all the professors thought I was crazy because it was about life on Europa. But I'm going to have the last laugh because we're probably going to find it somewhere out there. We have, the Cassini and Galileo missions. They took all kinds of samples and images and spectrometer readings, et cetera, of Europa and Enceladus. So what do the astrobiologists in the audience, on the panel, think about the possibilities and what have we found that would point to there possibly being life on those moons or any of the other satellites in the outer solar system. Dr. Abramovich.
Okay, I'll take it. I was hoping for Carol to to speak. So from what I've known and from what I've read, basically what we are finding is that NASA had this strategy of follow the water. We did find a lot of molecules of water also on Europa, but also on Enceladus. And what we're looking for in Europa is that we have figured out that underneath 15 kilometers of ice, which is a lot of ice to go through, there's probably a liquid ocean, which is very, very salty. That's the reason why it's liquid, because, you know, Europa is so far away from the sun, and temperatures are super low. And so, and also we are familiar with the environment surrounding Jupiter, which has a lot of a really strong magnetic field. And so we're thinking that these areas, and we're looking at the ice covering Europa, we see that it's formed relatively recent, and it's changing, it's dynamic. So there's a dynamic process going on beneath the ice that then push out new ice to the surface. And hence, once we have this combination of having a liquid state of water, and we have an energetic source in a dynamic place, then we're thinking that maybe perhaps underneath the 15 kilometers of ice, there's enough shelter, there's enough energy for life to evolve in the planet itself. Again, from planet Earth, we know that there are places which are very happy to live in the dark with very little sunlight whatsoever, and they're able to do chemoautotrophs and chemoheterotrophs, and we know that we're very happy using nutrients and other energy sources than light. That's what I know about Europa at the moment. I don't know about any missions going to Europa, which is sad, but I hope it will happen. It takes about 8 years to get there, so it's a really long mission.
I think the Europa Clipper is on the table. They're planning a mission.
Yeah, I don't know if it's going.
Orbiter. That is an orbiter mission. It is not a lander. There was going to be a lander. There was a lander that was pushed by a congressman, actually. And there was quite a bunch of research and study and money was spent on developing that Europa lander. And then that congressman lost his re-election, and that actually put the kibosh on it, which is actually, in my view, a good thing, because it was a very optimistic, success-oriented sort of program, very much in the vein of Viking, that we were going to go to Europa and find life when we hadn't really ever gotten good even imaging of the surface, good enough imaging to know where to land the thing. And Europa is extremely, because of the Jovian magnetic field and the charged particles trapped in the Jovian magnetic field, Europa is an extremely hostile environment. So hostile that this lander was designed to self-explode after a month, so that Europa could not be contaminated by microbes that might be hiding on the spacecraft if the spacecraft were to die because of the high radiation environment it was sitting in. So it was, in my view, it was very unlikely to find life on Europa, because I think it's very unlikely to be there. Certainly on the surface, sitting in this, nuclear explosion level radiation environment. And that it was going to be a complex mission that had a very, very short lifetime. I'm much more optimistic about Enceladus as a life detection target. And Chris would probably be the better person to talk to about this, because he's been the PI of a New Frontiers level mission to go sample plumes of Enceladus. So Chris, why don't you take it away?
Yeah, Carol was a co-I on that mission. It was a concept to fly to Saturn. Enceladus is a small moon of Saturn, and it's really come to the fore in the question in terms of life detection, because Cassini discovered in 2005 a plume of water coming out of the ice in Enceladus not just water, but organics containing nitrogen compounds, carbon compounds, obvious sources of biological energy. All the requirements, all the major requirements for life are checked, and the samples are coming out into space at a flux approximately equal to the flux of Old Faithful geyser in Yellowstone Park. So all we got to do, so to speak, is fly through that plume, collect the sample. We know we'll get water. We'll know we'll get organics. We know we're going to get material coming from an ocean that's in contact with that hydrothermal system. So Enceladus, to my mind, is the target in the outer solar system for a search for life. And so we are pushing hard on that still. We'll try to put another proposal into New Frontiers to go out there and collect material in that plume and search for evidence of life. In that sense, it is part of the same intellectual exercise that searching for life on Mars is. It's addressing the questions that Bob put forward. Did life start on Earth? Did it come here from elsewhere? To me, that is a compelling scientific question. How do we answer it? We're not going to answer it on Earth. We're going to answer it by comparing life, if we find it on Mars and Enceladus. And as I said before, if those three worlds have life that maps onto a single tree, well, we know that life came here probably in an interstellar comet during the formation of the solar system, like Borisov, the interstellar comet that came through our solar system just a year and a half ago, right? Shedding interstellar dust throughout our solar system. Or if we go to Mars and Europa and Enceladus and Earth and find three different types of life, Earthlings, Martians, and Enceladusans, each with their own distinct biochemistry and genetic code, well, that would tell us that the universe is a wonderful place with all sorts of life forms. Life is easy, it pops up wherever is suitable conditions, and you know, it's a great place to live. We'll see.
Speaking of great places to live, for the astrobiologist on the panel, ice has been found in the permanently shaded craters of the moon and now of Mercury. And I believe the last I read, the ice on Mercury has this organic sheen over the top of it. Is it possible for any microbes to eke out a living in those ice interfaces where it's, you know, on the edge of the ice where the sun is, maybe a little liquidy?
In my view, the answer is a resounding no.
Okay.
So the ice would only be there, certainly on the moon. The ice is only there because it's at 50 degrees Kelvin or something like that. I mean, it's extremely low temperatures and it's sitting in vacuum. I mean, there is no atmosphere. So there is no liquid state possible, even if you could warm it up enough to have it start sublimating. It doesn't go through a liquid stage. So there's no way that anything that we identify as a life form that uses liquid water as its solvent to live in that kind of environment.
Okay, thank you. And I think we might have a little more time. I have several questions from audience members and from a variety of places. I wanted to ask about the perchlorate on Mars. I know that the Viking 1 and 2 labeled release experiment, there's some, you know, we're still going back and forth. Was it life? Was it not? Et cetera. And I know the perchlorate had something to do with that. Can you discuss why that would have affected the life detection experiment?
Perchlorate itself did not impact the life detection experiment. I don't think anyone has actually argued that. Chris, am I wrong about that?
No, you're correct in the terms of the 3 biology experiments.
Yeah.
But it did impact the results of the GCMS.
Okay, the gas chromatograph mass spectrometer.
So what Viking, the contradiction on Mars at the time of Viking and up until really quite recently was that no organic compounds were being found. You know, life doesn't just have its own little the cells, there's all the dead cells. And it builds up over time a organic burden. And without that organic burden, being there at all, detectable at all. It was felt by the Viking scientists, most of the Viking scientists, that there couldn't be life there. So that the signals they were seeing had to be some kind of a chemical reaction. And the signals they were seeing behaved more like chemical reactions than biological reactions, in the sense that as soon as you put the nutrients onto the soil, the reaction occurred. Whereas with biology, usually you have to create the exponential growth. So the initial reaction is going to be a few microbes, and then they're going to make more microbes. And so over a course of a few days, you make a big enough colony of microbes that they'll start making a signal that is a strong signal, but you don't see it initially. And on Viking, when you poured the nutrients into the soil, you saw the signal immediately. And then over time, over a few days, the signal kind of leveled off and even died off. So that didn't behave in the way that you would expect microbial growth in soil to behave.
Which would be less immediate.
Right.
Because it would have to metabolize, et cetera.
It would have to grow up more organisms, basically.
Oh, thank you. So what are your thoughts on recurring slope lineae and whether they are salty brines? I know there are some controversy over whether they're salty brines or ice moving or rocks moving down the slopes. What are they salty brines? What's the consensus?
Well, that has been, that story is still evolving. It's kind of been in flux. The latest results show that the recurring slope lineae are apparently thermodynamically triggered. They happen at particular times of year at particular temperatures, but they don't appear to be lubricated flows in the sense of having enough liquid water to actually change the slope that the RSLs would go down. So
we have about 5 minutes.
Okay, so basically they behave like dry flows. They only flow to the angle of repose. And if they were lubricated, they would go down shallower slopes. So it really is still kind of a puzzle of what's causing those things.
Okay, so since we have 5 minutes, I want to ask one last question, and then I think we have some Q&A in the queue that I'll get to for our remaining time. What is your for each of you, percentage of possibility extant life on Mars? Dr. McKay.
I would say the chances of extant life on Mars are small, tiny.
Okay.
I'd say 1 in 1,000.
All right. Dr. Zubrin.
I'd say 75%, because there certainly was life on Mars at one time, if from no other source than the Earth, because Mars had liquid water on its surface when there was already life on Earth, and it would have been inseminated from Earth if from nowhere else. And then as the conditions on the surface deteriorated, it would have retreated into the groundwater. So that's my leaning. I think that there probably is life in the groundwater of Mars.
Okay. Dr. Abramovich?
I think that just as I think that the universe is, I'm optimistic, I think it's filled with life, but I think that because it's so far away and because we're not up to it from a technological point of view, as long as we're not digging really deep into Mars and in several places and doing a proper mapping from a biological perspective, I don't think we'll ever find life on Mars at this rate. That's what I'm thinking.
Yeah, we're not moving fast enough. And Dr. Stoker, what do you think?
Well, I'm closer to Zubrin. I believe that if there was ever life on Mars, there's life on Mars now. Whether it is widespread or not, I think is really the question. And I think it's very likely to take a concerted program to find it. I'm pretty optimistic about the polar ices as a first cut, but if that were to turn out to be a negative result, then I think you are probably stuck with looking into the deep subsurface where there are plausible pockets of liquid water. Now, I have to say that the lake that has been identified under the South Polar layer terrain is not a habitable environment. Just the fact that you have liquid water does not mean you have a habitable environment. And that there is a lot of the scientists who've looked at this don't believe that that's what they are even seeing a liquid water environment, because the temperatures that should be at are way lower than would allow a liquid, even if it were a eutectic solution of perchlorate. So if it's being kept liquid, it's being kept liquid by some kind of a hot spot in that location, or it's some misinterpretation of the data.
Okay.
1 minute.
Oh, go ahead. Oh, 1 minute. Okay, so Daniel Tompkins asked on the feed, do subsurface microbes have a significantly larger biosphere than surface microbes? I guess on Earth.
Well, most of the Earth is underground, so they do.
Okay. All right. I'm just reading the questions. All right, let's see. A lot regarding Enceladus and Europa, the observation from, okay, Arthur C. Clarke, then, okay. Well, we have about 10 seconds to wrap up. Any final thoughts from any of you? I just want to say, first of all, thank you so much for joining this panel. It is a very important work you guys are all doing, and I appreciate it. And I agree, probably 75% chance of extant life on Mars. That's my specialty, and that's what I've been working my whole career to help prove.
I'm happy to find dead life on Mars.
Yes.
Dead or alive, it's fine. In fact, dead is preferred. Very much fewer planetary protection issues. Hooray for being dead.
We're all moving.
Well, let's go see what's there.
Yes, let's go. Thank you, everybody. Have a wonderful weekend.
Thank you very much.
Thank you, Nicole.
Thank you. Amazing work. Thanks.
Thank you.
Ciao.
Bye.
Bye-bye.
Bye.
Thank you to our panelists. That was a very enjoyable and lively discussion about the possibilities of life on Mars. Our next presentation is going to be from Nandin Erdin-Shatar. He is going to speak to us about the Mongolian Aerospace Research and Science Association. Welcome, Nandin.
Thank you so much. I'm checking the microphone. It sounds clearly now.
Yes, that sounds great.
Thank you. So, ladies and gentlemen, good morning, good afternoon, and good evening. We are connecting from everywhere around the world. So, thank you for introducing. And first of all, thank you for Mr. Robert Zubrin and Mars Society team for granting us such an amazing opportunity to introduce our project during annual Mars Society convention. It's such an honor. So I'm going to talk about our current project, Mars V, today. So let me share my screen now. So can you see the presentation now?
Yes, that looks great.
Okay, so thank you. So I would like to start this presentation with a little story of how we found out the idea. So, sorry, technical thing. So please look at these pictures. So how do you feel about them? I guess somehow they might give you some impression about as if you are in a different planet. But the truth is, these places on the picture, they are all in Mongolia, especially in Mongolian Gobi Desert. So same like this, a few years ago, our founder saw a Mars picture by the rover. And first thing on his mind was, this place looks very similar to Mongolian Gobi. This is how he found out the idea of Mars V project. And then, after seeing the picture of Mars planet, he made a more deep research to find out, is there any other similarities between Mars and Gobi Desert? Actually, the result was amazing, and he found out, and we found out certain things. So in here, so here's the result. So Mongolian Gobi is the 5th largest desert in the world out of 2024. And it is the most identical place with the Mars, because climate of Gobi Desert reaches plus and minus 40 Celsius degree, which is very diverse as in Mars. And Gobi is not only special because of some certain identical points with Mars planet, but there are more statements which make Gobi unique, namely in terms of renewable energy. So it is a place with, Mongolian Gobi is a place with rich resource of solar and wind renewable energy. 1/3 of the world's renewable energy resource is in Mongolia. So these facts gave us a motivation and confidence to start our project Mars V last year. So in short, our project mission here is to prepare an environment that is the closest to Mars and train individuals to improve their mental and physical knowledge and to increase their teamwork and adaptive skill. For accomplishing that mission, we started our project with 3 main big establishments where take places in Mongolian Gobi deserts. So these 3 main establishments are first, Comprehensive Training Academy and Space Exploration and Development Free Zone and Satellite City. So I will give information about each of them now. So first and most important thing is Comprehensive Training Academy for Survival and Adaptation. So this academy will enable professional astronauts, pilots, and tourists to attend training at a complex center with Mars-like environment. It will have multiple facilities for training practice and preparation, and each facility has its own purpose to prepare people's mindset to survive on Mars. Actually, adaptive and survival skill is one of the most important skill that people should learn and practice before they landing on Mars. In fact, there are many places and programs to train human resource to land on Mars, but from the point of landscape and ecosystem, Mongolian Gobi will be a perfect place for that, for train human resource. And second main establishment is a free zone, space exploration free zone. So free zone will establish test field and facilities for international startup companies to test their new space technologies and create an integrated supply network for space technology development. In other words, there will be economically, legally, and physically favorable environment for testing and developing new space technologies to colonize Mars. And the last big establishment will be Satellite City. So definitely there will be a population growth following the first 2 establishments, Academy and Free Zone. So Satellite City will be a hosting place for scientists, entrepreneurs, and tourists. So here is our imagination and pre-planned image of how the academy look like and how Free Zone look like in Gobi. So in the next, I want to talk about what makes Mongolia distinctive. Earlier, I mentioned only Gobi's special factors, why Gobi is perfect place to accomplish this project. So now let's focus on why Mongolia. So Mongolia is a 19th big country, the largest territorial country in the world, and which is located in Eurasia, but it is a landlocked country. So the concept of landlocked country it seems like a disadvantage, maybe earlier, but not anymore. Because farther location from water will be the perfect to test space technologies, rockets, and vehicles, because it's so far from ocean, quite safe to test it. So although we have no access to ocean and water, we have access to space, open space, we believe that. And here is more advantages and special points why Mongolia is a perfect place to carry out this project. So Mongolia have 4 seasons, which is very diverse, and Mongolia is one of the lowest human density country in the world, especially Gobi is most uninhabited place and quite isolated. And 1/3 of the world's renewable energy resource is in Mongolia. So which means we can create enough energy to support the process, like operation of this 3 big establishment. And geopolitically, we are close to the world's 2 big economies, one of the biggest economies, China and Russia. And we are also a nuclear-free zone with a free market economy. And here is some legal advantages you can check on the slides. So in short, Mongolia has advantage to start this project. So in the next part, I will give information about international ties. So it's a giant project with big establishments. We need to keep a cooperative and tight relationship with both domestic and international partners. So let me mention quick about our team of Marsview project. So currently there are over 100 people are working for this project to making a research and studies such as Gobi landmark research and legal research and so on. And moreover, there are over 2,000 volunteers who wants to contribute to the project. So recently the project is getting very popular in Mongolia. So in terms of foreign relation, we have presented our project to global leaders. So last year, August, we presented our project to Donald Trump, and the next month, Vladimir Putin, and then Indian Prime Minister Narendra Modi. So this project is presented to the global leaders. Moreover, we also have established a cooperative and friendly relationship with the national space agencies such as JAXA, NASA, Roscosmos, and ISRO, European space agencies, and also the biggest Mars exploration communities, including Mars Society and MIPAC, IMEWG. So let me talk about, maybe some of you might wonder that our mission, connecting mankind's vision to reach Mars, sounds a bit vague or abstract. So let's talk more precisely about it. So according to a private Dutch organization, Mars One, there are over 200,000 people who had interest to travel to Mars. But in reality, we believe that there are millions and millions of people around the world who has interest in space travel and tourism. But currently, only 7 space tourists made 8 space flights to international space stations since 2000. The publicized price was ranged 20 to 25 million US dollar per trip. So in this case, people consider the space tourism is expensive and risky thing. So therefore, our goal is to reduce that cost of space tourism and maybe the 100,000 times with a high satisfaction. That's why we choose Mars for everyone as our motto. So we firmly believe that by experiencing genuine space exploration feeling on Earth, will positively impact on humankind's mind. Because according to some researchers, the world's population is expected to reach 9.8 billion by 2050, nearly 10 billion. But our world, Earth, has limited resources to feed this lot of population. So it will result in food crisis and water scarcity and power supply shortage. So these facts demand us to obtain certain survival skill, and not only to protect our nature, our Earth, but also to producing more resources, new resources on different planets. So in order to reside in Mars, in outer space, we need to have a very identical place like Mars on Earth to train mankind and to test space technologies for Mars exploration. So for this matter, Marsview project can be a great partner in your building the Mars city on the red planet. So we believe that before we landing on Mars, we need to practice ourselves and human resources on Earth. So I would like to end my presentation with a quote from Albert Einstein. So Albert Einstein once said that logic will get you from A to B, but imagination will take you everywhere. So as we know, as we can see, there are some big entrepreneurs like Elon Musk, Jeff Bezos, or Richard Branson. They are making history. And we are at Mars, we have a piece of gem that could benefit humankind's dream. Together we can do, and together we can make a history. Thank you. Thank you for your attention. Thank you so much.
Thank you very much. My name is David Haslam. I am one of the hosts for the Mars conference, and my camera is still not working. Anyway, thank you very much for your presentation. We've got a couple of questions.
I would also like to introduce my teammate, Tolga.
Oh, sure.
And he is with me to answer the questions. Yeah, you can answer the question.
Okay.
Ask the question, sorry.
Coming on?
Yeah.
I'm here just by your side.
Okay. Very good. Very good. Well, the first question is, what is the website? The Bruce McKenzie is asking what the website is. They're having trouble finding MARSA on the web. So you could bring the website.
Okay, I will share it to the chat.
Okay.
Yeah. Marsv.com. Mars-v.com.
It's www.mars-v, as in visitor.com.
Yeah, I will. Let me write it. Yes. Did you find it?
Okay, so Bruce, if you're on, if you want to have a look for that, and if you find it okay, that would be good.
Yeah, I'm sorry. Hey, David. Tolga here. I'm one of the members on the Mars V. Were you able to find the website? It's, yeah, exactly as you said, www.mars-v.com.
Okay, I didn't, but I'm sure I'll check it out.
Yeah, we can send a link. Or
yeah, I also typed it on chat, and I can share a link now.
Yeah, Bruce just confirmed the mars-v.com does work. Okay. Great. Thank you, Bruce. Okay. a question from Natso, tying back to Tabor McCullum's Biosphere II project. Could the fact that the Gobi Desert having much colder temperatures than the, say, Sonoran Desert give you any advantage to any scientific experiments?
Mm-hmm.
Well, we're currently in the very early stages of the development, especially when it comes to programs on research for Mars and space technology and etc. So as of right now, we can't give you 100% sure on a comparison or any certain types of advantages at the moment.
Okay. Okay. From a personal standpoint, I'm sure the lower temperatures will give you a closer analogy to Mars, even if it's not all the way to an extremely low temperature, but yeah. And again, a personal question.
Yeah.
Sorry?
Yeah, I mean, of course, there are more hottest or coldest, more colder and hotter desert than the Mongolian Gobi Desert, but as like a very diverse, both hot and cold, reach from -40 to +40. It is Mongolia. Mongolian special thing is it is both cold and hot in the year.
Okay. Good. I see that Jarek Micah has joined the panel. Do you want to ask your question? Have to unmute first.
No, thank you. I will just join before our panel, which will start in a couple of minutes.
Okay, no problem. I have a personal question. So for the initial academy for the Gobi Desert, how are you planning to organize that? As a physical on-site academy or online or a combination of both? And what's the approximate price range to join the academy?
Mm-hmm. It will be a physical on-site, first of all, and yeah, so price range. Now, currently we are doing a pre-feasibility study. So now we are planning that, like how much it will cost to build the establishment. But for paying for, we are still making a research on that. And currently about our team, our nearly 200 team members is divided to 19 teams, like specific teams about Gobi research and program making team and itinerary creating team like this. So they are making, still developing the programs in the academy, and then they will also calculate how much it will cost to participate.
Okay, very good. Okay, we don't have any other questions at this point in time. But didn't, in the past, this is again a personal question because there's nothing else coming up, didn't Mongolia fly an astronaut with Soyuz missions a long time ago?
Yeah, 1981.
Okay.
5 minutes.
Mm-hmm. Yeah, and our first and only currently astronaut of Mongolia who went to space with Russian team in 1981 is our working as our advisor for our project.
Interesting. So is there a, because I know the astronauts are American and Western, cosmonauts are Soviet, cynonauts are Chinese. Is there a special name for Mongolian astronauts?
No, so Mr. Gurakcha, who flew in '81, is classified as a cosmonaut.
Okay, very good. Interesting.
So if you have a more
Quite a lot.
question and want to know more about our project, you can visit our website and see the contact information there. And we are willing to answer every question of you, and we are willing to give more information if you want later.
Very good. Well, I know I'll be in contact with you. I'm very interested in this.
Thank you.
So thank you very much for your time. I believe, well, we still have a few minutes, so let's see. Still got plenty of people watching too. So are you guys currently in Mongolia then?
Yeah, we are. And if we have a few minutes and there's no one to ask questions, so I can give some details about also our foreign honorary advisors. So it is a very big project for Mongolians, but it's a very big ambition for us. So currently we have nearly 10 foreign advisors. 10 foreign advisors, honorary advisors, who are experts in the space industry.
Okay.
So yeah, one of them is Elisa Carson, maybe all of you know, and she is also one of our advisors. And when the time is, when the pandemic, the COVID situation will be okay again, and she and other advisors expressed they wish to come to Mongolia and see and visit the Mongolian Gobi personally, in person.
Very good.
We have 1 minute.
1 minute left.
Mm-hmm.
So what time is it currently in Mongolia?
It is midday, exactly midday.
Yeah, I'm actually speaking of Singapore, so even further around the world than you.
Yeah, that's why I was saying good morning, afternoon, and evening.
Yeah, very good. I appreciated this. All right. Well, very good. Thank you both very, very much indeed for attending the conference and speaking to us.
Thank you for everyone.
Thank you.
Let me mute.
Okay.
All right. Thank you, Nandine. Our next panel is going to speak to us about new space centers, and it consists of Jarek Mika. Jarek, do you have Christoph and Lucas with you as well?
Good morning, good evening, everyone. We are here together with Krzysztof, and I think that yes, there is Łukasz also on the other side.
Excellent. So Jarek Mika, Krzysztof Kakalinski, and Lucas Wilczynski. Welcome.
Welcome, everyone. And I would like to ask Łukasz to start our presentation, and then we will go with the PowerPoint presentation.
Hello, good evening, good morning, good afternoon, because I know that we are around the world. That's amazing. Ladies and gentlemen, and the fellow Mars Society members, I've been in Mars Society since 1997, and the next generation was always one of the most important target groups for all its activities and activities of space sector in general. Because whatever we do today, our activities, we are planning, go to Mars, etc., will be there present. And this is very important because we are right now working on the present day of our kids and our grandkids, etc. So, and this was one of the goals, of course, of European Rover Challenge we organized in Poland since 2014 to invite always the next generation to come, to inspire them, and to teach them. But this is organized only once per year. And the project we would like to talk about today will be absolutely boosting their passion every day. And this is amazing. When I saw this project for the first time, I was shocked because, you know, it was a project that really will have strong influence of the next generation. It comes from Poland, it comes from Europe, but I hope that this kind of project, this idea will also spread the world, because the idea is not only to have it in Poland in general. So I would like to, with this short introduction, present you a very tremendous project that me and Robert Zubrin are supporting. And ladies and gentlemen, I would like to present you the Space Science Center. Jarek, the floor is yours.
Thank you very much for this kind words, Łukasz. We saw that during the presentation, when someone tries to put some video, there are some difficulties. So what we will do, we'll switch to another way of presenting a movie. So you will see at the background our movie. So now, for now, I will just skip her for a while, and you will be able to see our movie.
Nie jeden z nas marzył o gwiezdnych podróżach. Aktualnie tylko nieliczni mają okazję poczuć emocje towarzyszące eksploracji kosmosu. Postanowiliśmy stworzyć miejsce, w którym marzenia o podróży w przestrzeń kosmiczną staną się rzeczywistością. Space Science Center to projekt popularno-naukowy z elementami rozrywki, który zapewni wspaniałą zabawę każdemu odwiedzającemu. Chcemy nim zainspirować nowe pokolenia naukowców, inżynierów, odkrywców i zdobywców planet. Nowoczesne technologie, roboty, symulatory lotów, laboratoria zbudowane zostaną na najwyższym światowym poziomie. Space Science Center goście będą chodzić po Księżycu oraz przebywać w marsjańskiej kolonii. Projekt powstaje w centralnej Polsce. Obecnie trwają prace przygotowawcze i koncepcyjne. Poszukujemy partnerów merytorycznych, biznesowych i sponsorów. Razem rozbudzimy wyobraźnię małych i dużych.
3, 2, 1.
So thank you very much for watching with us this short movie. Now we will switch to the presentation. That would be much better for further. So, ladies and gentlemen, thank you once again. As you have seen, this project is quite unique. First of all, I would like to mention that the fundamental of this project is that we would like to run it as a non-profit project. Our main goal, of course, is this educational layer of this project. We put a strong attention to specifically to present difficult educations like science education, math, physics, and so on. We have approached to this with a quite innovative way. We have used the latest technology of the entertainment industry and combined that with a didactic layer. All of that is wrapped around the multi-story game playing, where everyone of the visitors will choose of their role, and they will be able to act as an astronaut, as engineers, as astro engineers, as biologists, and so on and so on. I would dare to say that this project is quite unique, even on a global scale.
Okay, some words about the location. So we have the great location in the center of Europe. I mean, in the heart of Europe. About 500 kilometers from Berlin and 100 kilometers from Warsaw. we plan to build site for our project. We have the perfect access to the highways from the north to south, from the east to west, and also we have perfect connection with the airports and the trains. So we are sure that this is the great location for our project, for the unique project.
So, as I have mentioned before, everyone will have a different hobbies. I mean, some of us would like to be an engineer, some of us would like to be astropilots, some of us would like to be just an ordinary tourist. Of course, most of us, especially here on this panel, would like to go into space. So what we have designed is that in our facility, everyone would be able to execute their hobbies. So first of all, when you enter our facility, you choose the role that you would like to play. So if you would like to be an astronaut, you choose a role as an astronaut. If you would like to be just an ordinary astrotourist, you choose this kind of a role. Then the system will get you through the whole path. It will be a specifically designed path of the test, exams, and knowledge that you have to acquire in order to become an astronaut or a tourist. So we will teach you the basic of the solar system. We'll get you through the tests and experiments, but they will be given in a really, really pleasant way. We'll teach you how to move around the International Space Stations. Of course, if you would like to become an astronaut, we'll perform some endurance tests. Once you will go through all those tests, and we'll find out that you are ready for a next phase, there will be 3 rockets ready for you to take you into the space. So once we will go up to the space, you will be able to drive on the moon, to visit the planets. We'll have a specifically designed area where you will be able to steer the robots which are currently running on the moon or on the Mars. Even there would be a specifically designed area where you can drive them. We have a really astonishing dark roller coaster. These dark roller coasters will take you close to the black hole. You will experience its incredible attractions. And thanks to our ultra-modern device, you will be able to get very close to the event horizon. Of course, nothing happens to you, but then you will be able to feel it. We'll take you very close to the erupting plasma from the sun, or you will be snaking through the asteroid belt. We have designed more than 10 laboratories in which you will learn to build satellites and conduct experiments. You will learn physics, mathematics, and chemistry in a very, very pleasant way. Finally, when your training is over, we'll embark on an amazing journey through the universe. In our 360 cinema, you will experience a journey with every sense. That is a kind of a summary of the journey in our facility. We'll say goodbye to all the visitors by performing a great concert by the robots. Each participant during this event will receive their certificates and diplomas, which will confirm their trainings. And what is more important, they will get a kind of a guidance, what they should do next, what they should focus on in order to finally, when they grow up, to become an astronaut or engineers and so on. So that would be a kind of a summary of our visit in our facility. Lucas, back to you.
Yeah, so as you can see, this is tremendous, really. As you can see, this is a huge project that will help actually, as I started, the next generation, because since the beginning of the space program, about 550 people traveled to space. And by that project, we would like to definitely raise that number to what you can see. It's 380,000 people every day. Okay, virtually, using a special platform, but this unique place will fortunately help people boost passions and boost interest in space for the next generation. And the next generation, someday, me and Lucinda called Marsonauts. And this is actually, I don't know, Lucinda, if you are watching us, but this is the place where Marsonauts will be raised. So this is a place that will really boost its passions. And of course, you saw many entertainment things inside, not only science, but also entertainment. But for these young kids to learn and have fun, and to have fun and learn, this is something what can actually mean the modern education for them.
Thank you very much. Okay, and now some main information about the project. The budget which we planned is $42 million. And in this value, we include building infrastructure, equipment, and audiovisual content, of course. We don't forget about the kitchen, for example, and the restaurants, because it's also really important in that type of the project. So we want to build and see the facility in the 22 months. This is obviously longer than the flight to Mars, but in the investment reality, it's a very good result. We plan that from tickets and the products in the Space Science Center will bring good finance results. So I mean, the EBITDA, expected EBITDA is around 38%. After first phase, we are planning extent of our project, and we want to add next phases.
Then excellent. So here you are. You have met Jarosław and Krzysztof, the co-founders of Space Science Center. Of course, every project has got to have additional support, and by that we joined it together with Robert. We joined the project as project ambassadors to bring the news to the world. Right now, we also have a very strong content support in Poland. So we have Adam from Copernicus Science Center. We have Karol that is one of the, we can call it space funded in Poland, but he's very exceptional person who speaks a lot in media in Poland about space. He's always a host in European Rover Challenge. And we have also Radosław, one of the bloggers in Poland. These people will help us to work on the content, to work on every piece of exhibition. But this is only the beginning, as you can see. And by every stage, we'll have more and more people waiting in the line to join us. And of course, if there is anyone from our viewers who would like to join us as well to help us in this amazing project, I think Jarosław and Krzysztof are very open for that as well.
Of course. Thank you, Łukasz. So in every project, we need the strong partners. So also here we have the Mars Society as a partner, the European Space Foundation, and especially thanks to you, Łukasz, for your support. And Mars Society for us is a really important partner to share the information about our project and also support us with some ideas, some knowledge. In Europe, also we have good partners, business partners. For example, Platish Group is a co-producer of the Witcher series responsible for the content. So as you can see, in Europe also we have good companies about the robots, simulators, immersive tunnels, and I mean about the three companies. For example, it's KUKA Robots, Simurgs, and Simtech. And of course, we are looking, as Łukasz mentioned, we are looking for the new partners. We are really open for the cooperation. So please join us and visit also our website for the more details.
So that would be all what we have prepared for ourselves, for you. So if you have any questions, we are open and happy to answer them. As Krzysztof had mentioned before, we invite you to visit our website. You can see more details about the project. But when you will have any questions, we are happy to answer them.
Yeah, thank you very much for the presentation. Curious as how long you're planning each experience to last. Is this going to be an all-day affair, or is this over multiple days?
Thank you very much. We were thinking about that, how to do that in a proper way. And we choose that we will do that in stages. There will be a 3-hour trip. And once you will enter our facility, you will receive a special device, which will be monitoring your progress, but also will limit your oxygen. The oxygen will be only for 3 hours. So we have planned all those tours for 3 hours. And this is also planned that you cannot adapt so much knowledge in such a short time. So we have planned that and we will invite everyone to come back to deepen their knowledge and deepen their experience in our facility.
So maybe I will add also important information. So in the one moment, we can have 2,000 people in our project. So the capacity of the day is even 8,000 people.
You said 8,000 per day?
Yes.
And this is
yeah, actually, the full capacity of our facility would be around 1.5 million people per year. But at the beginning, we are assuming that there would be 1/3 of that visiting. This is kind of a safe assumption, but I would say on the other hand, quite interesting for the investors in terms of the payback.
Question here on this is this proposed for children or all age groups, and how does the curriculum change between your age and experience?
Yes, we have designed this facility for visitors from 3 years old up to 99 plus. And of course, based on that, as I have mentioned at the beginning, that you will receive a special tool, and based on the data that you will provide, the system will put you through a dedicated path. So if you are a really small child, you won't go through the endurance tests and so on, but you will be able to visit some laboratories, some kids' playground, and so on. But if you are a little bit older and more mature, you will be put on a different path, and a different experience will be given to you.
Sounds good. Do you have an idea on how much this is expected to cost?
Yes, and I think Krzysztof could answer that question very good.
Yeah, so the budget, our capex is $42 million, more or less, because this is the roughly calculation. Of course, when we started, we can check and to verify everything, but in our assumption is $42 million.
And I can add that perhaps that would be also interesting for the visitors. We are expecting to have the ticket per person, per adult person, below $20. So that could be quite affordable for the families.
Is this designed to go through as a family, or is it individual tracks based on?
That is individual per adult person for $20, and for the kids it's half of the price. So I would say that you can go with the four people family under the $50 here around.
Great. And how far into development are you? Do you have an expected launch date or a proposed one?
Not yet. That is too early. We have acquired the land. We have secured something like $2 million already for this investment. But still, as you can see from the budget, it's still far to go. So once we'll secure at least 30% of this investment, we'll set up the date. At the beginning, we know that all the design phase and building phase will take us something like 22 months. but not yet. We have not set a starting date.
Gotcha. Do you have any plans for how to update the training courses that you're planning on as as data and science changes?
Yes, this is why we are mainly at this conference. We would like to join. We'd like to ask all the people from the science world to join this project and to be on the current version. We know that it will be a live project. As you know, the sequence of the conquering the space most probably in a couple of years will be that first we'll land on Moon, but then we'll go to the Mars, and that would be as well in our facility. The first stage will take us to the Moon, but we are already having plans the second phase and third phase, and the second phase will be conquering the Mars. So as it will develop in the real world, we would like to also adapt our facility according to that. And of course, our trainings and educational path will have to follow that.
Gotcha, that makes sense. So are these going to be separate sections of the location, or is it going to be all inclusive? How does that work?
Yeah, we have secured 20-hectare plot in Poland. Actually, the first phase will just consume 3 hectares. So we'll have still 70 hectares space free for next phases. So we are quite on a secure basis for further development. And we are planning to add additional buildings on the next phases.
Makes sense. Does anybody else have any questions? I'm not seeing any more questions pop up. Do you guys have any closing statements or anything else to add?
Yeah, I will just ask. I will just give a few words, and then I will ask Łukasz to wrap up our meeting. So first of all, I would like to say thank you for the Mars Society for this opportunity to speak to you, to present our project. Honestly speaking, that is the first time we came out public. We are working on this project already 1.5 years to prepare everything, to design everything. And finally, we take a decision that we are ready to go out. So once again, thank you for the time, and thank you for listening to us. Thank you for all those questions, and back to you, Łukasz.
Thank you, Radek. As you can see, thank you for all the good questions. I know that we could talk about this project for more like one panel, but this is really a long talk. It will be a long talk, but generally, as you can see, it's very deep, connected with Mars Society already. It's got me from Poland. It's got Robert already on board. So as you probably see, and it's live. It's live. This project is live. So as one of the questions was about updating the thing, it will be actually the paradise for all the Mars educators, because if you have any idea and you would like to realize this idea to come in true, then I think the Space Science Center is the place that this idea will be materialized. Of course, Jarek didn't mention one thing regarding one of the partners, the Platish Image. It's not only will be connected with visual content. This is the company responsible for the whole animations you could see, for example, for Rosetta, for ESA, also working for NASA. So the same type of animations, the same quality that are using by the space agency will be used here as well. So this will be very high quality of attraction, the very good immersion. So I would not like to prolong this my speech, because I love this project and I would love to talk about this 1 more hour. But generally, visit the website. If you have any ideas, just mail to us, and we will work with you on this project, because this project is not only a space center, it's surrounded by non-profit project, and will be open to any of us from Mars Society to give our knowledge, to give our ideas to this. And maybe it's not only one space center that will be built, but this is something we are living right now.
Thank you very much, Lucas, and thank you all for listening to us.
Okay, great. Thank you. And we had a question also that you just answered about how we can support you. And I think going to the website is the perfect way to do that. So we'll make sure and do that. And once again, thank you for your time in the presentation.
I have a quick question. I just thought of it. Sorry.
Yes.
This is David. Who do you class as your competitors as far as attracting families to come to your center?
Sorry, you said who are our competitors, yes?
Yeah.
Oh, okay. So I would say that is actually a very good question, because this type of industry in Poland is on a quite a boosting stage. We have not so many this kind of facilities in Poland. They are just opening right now. And each year, the number of visitors are progressing with 2 digits percentage. So in something like between 10 and 30%. So in a sense, we have a competition because we have a science center, very good one in Poland, which is a Copernicus Science Center. But on the other hand, it is quite different because we are providing this knowledge in a little bit different way with lots of entertainment. So on the other hand, we have entertainment facilities in Poland, which are attracting something like 1.5 million people per year. But on the other hand, those entertainment facilities are not providing the science. So we managed to combine those two things to provide entertainment and education at the same time. So in fact, the direct competitors we do not have with this type of a project, but you can find some parallel attractions in Copernicus Science or another facilities, entertainment facilities.
And then a follow-up question, topical. Have you started to consider the problems involved with the post-COVID period?
Yes, of course. That was actually at the beginning of the COVID. We already saw that could be an issue for our project. So we have already in our plans a kind of a contingency plan. What will happen if the COVID will develop even more further than it is now? And to answer your question, yes, we do have a backup plan. We have how to approach that. And still maintain the visitors which will be visiting our facility and implementing the really high standards of hygiene. And also we have a backup plan in terms of if we will be completely shut down by the, I don't know, government officials. We also can run our facilities still and provide this type of entertainment. Of course, a little bit different than visiting by person, but still, you can enjoy our facility.
Well, this is a joke, by the way. You have the ultimate COVID protection. You can put each guest in a spacesuit.
Yes, that was one of the ideas, but of course, taking into account the hygienic about that would be quite difficult to put into the suits so many thousands of people per day. But yes, that is an idea worth to think about.
Yeah, it was a not very funny joke. So
yeah, I know.
Thank you.
Thank you very much. So if there are no other questions, would like to say once again, thank you for everyone, and have a good evening in America, and have a good day in Europe.
All right. Yes. Thank you very much. Have a good day.
Have a good day.
Thank you, guys.
Well, we'd like to thank everybody for participating today and attending our plenary and our track discussions. As a reminder, tomorrow our morning discussions are going to start at 9 a.m. Pacific time with Barbara Belvisi, who is the founder and CEO of Interstellar Lab. We look forward to everybody seeing everybody there tomorrow.
Hey, this is James. Are we all good? All done?